Okay. Yeah, hi, good evening, everyone. Welcome to the open session of week 7. Okay, now the one message I have received in the chat. One second. Now that we have 200 this one, now we move to the vertex next. Okay. Yeah, so one thing I want to just suggest that actually what we generally see in the previous terms, if someone got good marks in the quiz one, okay, so they generally actually takes some rest or take break and just this feel like that the PDSA is easy. But in generally in quiz 2 actually we get the lower passing percentage in the quiz 2 exam. Okay, so suppose in quiz 1 we are getting 80% passing uh, result, and suddenly this in quiz 2 it reduced to till like 50%. Okay, so don't take this just take this seriously. Okay, so this is the main part of the PDSA, week 5 to week 8. Okay, and just give proper time for the each content of the week 5 to week 8. Okay, so don't take light this part. Okay, this will also helpful in the end term exam. Okay, so just give more focus in this part of the course, week 5 to week 8. Okay, so I think in the previous session, week 6, some part is already discussed. Can anyone tell me what is the remaining in week 6?
Binary trees are, I think,
Okay, binary search tree.
yes, binary search tree.
Okay, okay. So that means heap and the remaining part is already discussed in the previous week
Yes,
session.
Heaps was discussed in the previous class.
Okay, fine. Okay, so today we will start from the binary search tree, and we so there is some part of the binary search tree is discussed in the week 6, and the continuation part, okay, AVL tree, which is discussed in the week 7. So we will discuss both. Yeah, any before starting, any query from anyone? Any specific doubt in week 7 or week 6?
So today we are going to cover week 6, right? Because I think we skipped week 6 because of the quiz one.
Okay, today we will cover one topic from the week 6 and then week 7. Okay, and previously we have, so last week actually, Bhaskar have taken the session and he discussed the remaining topic in details. So if you have missed that, you can just watch the session again. And if you faced any problem, then you can ask in the next session. Okay, just watch the previous Wednesday session. Okay, so we will discuss from the binary search concept of the big 6, and then we will discuss the big 7. Hmm. Okay, so big 6, yeah, binary search. Okay, so the next data structure we will discuss is binary search tree. Okay, so as per the name, this is also a binary tree. That means it can have maximum 2 child. Okay, minimum maybe 0. So what is the things why we are creating this binary search tree, and what is the benefits of this binary search tree? Okay, so let we will discuss these things. So suppose if we are maintaining the data, okay, so where the data is actually regularly changing, okay, not the fixed data. If we are continuously changing the data, updating the data, and removing the data, this type of things happening with our data. So that type, in that case, so what type of data structure is actually useful? So that means we are regularly performing some operations like insert operation, remove operation, delete operations. So that operations should be performed efficiently. Okay, so how we can maintain our data in that way, so we can perform these operations, general operations, efficiently. That should take less time to perform. So this is the data binary search tree. Okay, and binary search tree is also a non-linear type of data structure. So what is the definition of this binary search tree is basically, so in the next part you can see the definition. So this is also a, first thing, this is a tree. Okay, you have already seen the tree definition in the previous week. A binary search tree is a binary tree that is either empty or satisfy the following condition for each node v in the tree. Okay, and what is the condition? Condition is that the value of the left child. Okay, so value of the left child or left subtree. Okay, so that means left to, value of the left child and each node in the left subtree is always less than the value of current node v. Okay, and in the reverse way, the value of the right child or the nodes in the right subtree is always greater than the value of current node v. So this is the definition of binary search tree. If we draw the diagram, so we can simply understand by the diagram. So let me just give the example. So if I'm creating a node, so for example, this contains the 10 value. Okay, so left child, we will always store the smaller value for corresponding to this 10 node. Okay, so like 5. Okay, right child will always contain the greater value compared to this parent node. Okay, so like 20. But this is not the only case. We will also maintain one another property. So all nodes which are coming on the left subtree of this 10, that should also be a smaller. Okay, so like this one and this 7 and this side 15 and we can 25. Okay, so now you can see the definition. So if we talk about parent or child relation only, okay, so that relation will come, left child will less than to the parent and right child will be the greater than to the parent. But also left subtree all nodes values should be smaller than to the parent or to the current node. Okay, if I'm considering this as a current node, so right side, all the nodes which are coming on the right subtree. So subtree means this complete part is the right subtree of the 10 node. Okay, so all values should be greater than compared to this current node 10. So these two properties should be fulfilled for the each node. Okay, so if we check this subtree part only. Okay, so this time we are checking only this subtree part. So same things, the right side of this 5 should be greater and left part should be smaller, all the values. Okay, so this property should be maintained. If we maintain this property in our data structure, so we can take the benefits of the operations like searching, insertion, and deletion, all these operations uh, by the efficient way. Okay, so we can perform these operations in the efficient way in the less time. Okay, so this is the main things. Now the come to the how we can create this type of data structure and how we can perform the operations, and then we will discuss the things. So first thing, if we are getting some data, okay, so the sequence of numbers. Okay, so like 10, so insertion sequence can be anything. Okay, so data is coming in any order and we will create this data binary search tree. So how we can create this binary tree? So logically we will understand this. So suppose we have one sequence. Okay, like 25 6 3 1 8 25. Okay, so now suppose this sequence is coming for the insertion and we will insert this sequence in our binary search tree, and we will create binary search tree. Okay, so initially we have empty binary search tree, so there is no node in our uh, binary search tree. So that means this is empty binary search tree. So first node when we are inserting, so definitely this node will become a root node. Okay, so we will insert this node because there is no node before that. We will insert this value as a root node in our binary search tree. After that, we will take the second element in the sequence. Okay, so now we are inserting this 20 in our binary search tree, existing binary search tree. So what is the procedure of insertion? We will always start comparison from the root node. Okay, we will always start from the root node, and we will compare the elements, and based on the value we will move. Okay, we will move. Suppose if we are getting if when we are comparing the current element for the insertion with the root node, if we are get this current value is greater, then we will move to the right side. Okay, if the current value is smaller, we will move to the left side. So in that way, we will traverse in our existing binary search tree, and at any time when we are finding empty place, okay, in this traversing, at any time if we are finding empty place, we will insert that element at that place. Okay, so now 20, this 20 is coming. Now 20 we will start comparison from 10. So 20 is smaller or greater? 20 is greater. So we will move to the right side, but right side is empty. There is no child, okay, on the right side. So that means we are finding the empty place on the right side of the 10. So we can insert this as a right child of 10. Okay, now this node is inserted. Now this is a one binary search tree. Now next element we are getting 5. So 5 we will compare from the root node. Okay, so every time we will compare from the root node. Now 5 is smaller than 10. Okay, so if we are getting smaller, then we will move to the left side of the 10. So left side there is no child connected. Okay, so that means this is empty place. We will insert 5 on our left. Okay, so this 5 will insert as a left node. Now 6, next node is 6. 6 we will start comparison from 10, that 6 is smaller than 10. Then we will move to the left side, but left side child node is available. Okay, now we will repeat this comparison process with the child node. Okay, so 6 is smaller than 5 or greater than 5? Okay, so 6 is greater than 5. So based on this value, we will move to the right side of this 5. So right side is empty, that means there is no right child of this 5. At that place we will insert our 6. Now next node is 3. Same things we will repeat from the 10. 3 is smaller than 10. Now we will compare with the left child. Now 3 is smaller than 5. Then we will move to the left side, and left side is empty. So we will insert at the left child place 3. Okay, same things from for the 1. 1 we will compare from the 10. So this is smaller. Then we will compare with the 5. It is smaller. Then move to the left, and we will compare with the 3. Okay, so 1 is also smaller than 3. Then we will move to the left of 3, and now this is empty place, and we will insert 1 at this place. Okay, now for 8. So for 8 is smaller than 10 but greater than 5. Okay, then compared to the 6, so 8 is greater than 6, and we will move to the right side and insert here. Okay, now 25 is greater than 10, and when we compare to the 20, it is also greater than 20. Then we will insert of the right child of 20. Okay, so finally, in that way we will create a binary search tree. Okay, now you can see the property. So this tree is actually maintaining the property of binary search tree. So you can you can select any node, and you can compare the right subtree and left subtree part. So it is managing the property or not. Okay, so this is the process of insertion. Insert the node. Okay, it is clear. So if any sequence is given, so in exam actually this type of question is also asked in the previous terms. One sequence is given, so just create the binary search tree. So this part is clear, how we can create the binary search tree if any sequence is given?
So yeah, so this part is clear, but one thing we observe here is even in the non-leaf node, it's not full or complete. There are still
Yes.
empty spaces. That's the thing we observe.
Yes, correct. So that happen in the binary search tree. So here we are not filling label by label. Here we are filling this. We are creating this binary search tree based on the value. Okay. So that some place may be empty. So that part will come after this topic. So what is the disadvantage of this binary search tree when we are creating this binary search tree in that way? Okay. So insertion part is clear. Now if we suppose create the binary search tree, and what are the advantage of binary search tree? Okay, suppose our data is maintaining in that way, we can search any value in lesser time. Okay, so you can see in this binary search tree, so which we have created, how many elements are there? 3, 3, 8, sorry, 3, 3, 6, and 8, total 8. Okay, so if suppose if we store these 8 elements in normal list, okay, so what is the maximum time required to search any elements? Okay,
Eight, eight
8
linear
element,
search. Yeah,
8 element linear search. Okay,
yeah.
but if we are storing this 8 element in our binary search tree, so I here there actually we are maintaining some order. Okay, so we can find any element in lesser time compared to the linear search. Okay, so suppose you can pick any element in this data structure, you can pick 8. So how many steps are required to find 8 in our data structure, this in this binary search tree? So same process which we are using for the insertion, same process we will use for the searching. Okay, we are finding 8 in our data structure, it is exist or not. So we will start from comparison from the root node, and then we will check 8 is smaller than or equal to or greater than to the current node. Okay, if it is equal to, then we can return the answer, yes, this is exist. Okay, if it is smaller than, then we will move to the left part. Okay, if it is greater than, then we will move to the right part. Okay, so for example 8, 8 is smaller than 10, then first comparison we are performing on 10. Okay, so 8 is smaller than 10, so we will move to the left side. So that means the all part which are coming on this right side will never compare with this searching element, so that part is removed totally. So next step we will compare with the 5. Okay, so 5 is 8 is greater than 5 or equal to 5 or less than 5. Okay, so based on that we will move. If equal to, if our value is equal to, then we will return the answer, otherwise we will move. Okay, so this time we will move on the right side of the 5. Okay, so second comparison is happening. So first comparison on the root, second comparison we are performing of the left child 5. Now this part is removed for the comparison. Okay, so now 8 we will compare with the 6. So yes, once again it is greater than, then we will move to the right. Now next time we will, so this is the third comparison, and this time we will compare with the 8, and now this is equal, and then we can, so this is the fourth comparison. Okay, so based on this height of this tree, we can decide that maximum number of comparison, how much many maximum number of comparison required. Okay, so for this binary search tree, you can see the height of, if we consider the height, the number of nodes in the max longest path. Okay, in our tree, so this is 4. Okay, our longest path in from root to leaf node is so the 10 to 1 or 10 to 8. Okay, so here 4 nodes are coming in this path, so we can say that the height of this is 4. Okay, and so maximum 4 comparison are required to find any value out of this 8 in this. Okay, so our data is maintaining in this structure, you can find, you can search any elements in
in 4 steps.
4 steps. Okay, so same things. Now this is one random example. Okay, suppose if I am getting this type of data structure like a binary heap. Okay, so our binary search tree is actually full binary tree. Okay, so all labels are full. So suppose we are getting like this type of. Okay, so like this. So here suppose we can maintain. So in four label. Okay, so 1 2 3 4. How many elements are there total? 15. 15.
Yeah, 15 to the power k minus 1.
Yes. Okay, so for 15 elements you can find any element in 4 steps, in 4 comparison. Okay, so this is one small diagram. If we extend this binary tree in the lower part, suppose if we just use the 10 label. Okay, so 10, this is first label, this is second label, this is third label, like. Okay, so if we use 10 label. Okay, so that means total elements will be 2 to the power 10 minus 1. Okay, which is 1023. And for to find any element in 1023 elements, you need to compare only 10 elements. That means in 10 steps you can find any element in 1023 elements. Okay, so you can see the benefits of this binary search tree data structure. In 10 comparison you can find any elements in your 1023 elements. So this will be very fast. Okay, so that means you need log n time to search any elements. If your binary search tree is look like this. Okay, full binary tree.
Sir, so in the first example, we'll have log 4.
Not log 4. Here n is the total number of elements.
Okay, but then we are taking 4 steps, not 3.
So this is actually random example. I'll come on that. What is the disadvantage of this normal binary search tree? So I'm talking about this full binary tree. Okay, when our all the labels are filled. Okay, in that case we are simply getting log n steps. Log n steps are required to find any element. Okay, but what is the problem of this normal binary search tree? Suppose our insertion order is like look like this. Okay, so 1 2 3 4 5 6. Okay, here we are inserting the elements dynamically. Okay, so our order can be anything for the insertion. So if your order is coming in that way. Okay, so we will create the binary search tree for this. So what type of binary search tree we will get? Okay, so 1 will come at the root node. Now we will insert 2. Okay, 2 is greater than 1. Then we will insert on the right. 3 is greater than 1, greater than 2. It will also come on the right. 4 is also greater than 1, 2, 3. Then it will also insert here. Then 5, then 6. So now we are getting this type of binary search tree. This is also a binary search tree, but this is looking at linear connections, like linear linked list. Okay.
This is the worst case. Basically, in the worst case, there are n elements. It'll have like n steps. This is the worst case.
Yes, this is the worst case of the binary search tree. When our elements are coming in the sorted order or unsorted order, we will getting this type of binary search tree, where the heights of this binary search tree is also equal to the n. Okay, if our number of elements are 6, so height is also a 6. Okay, so in this case there is no benefits of the binary search tree. Total maximum n steps are required for the searching. So this is in the worst case. You need to traverse all the elements on the right side, and out of these 6 elements, 6 comparison are required. So in general, binary search tree it's not much useful if it is not balanced actually. Okay, so we can say that this is not balanced. So balance means the height of the left subtree or the right subtree should be approx equal. Okay, for the each node, you can say. So then you can you may get the benefits of the binary search tree. If height is equal, left subtree of or right subtree height is approx equal, then we can get the benefits of the binary search tree actually.
So should we, when we are creating the binary search tree, just get the middle element, or
No, this insertion is actually coming one by one. So when one is coming, you are inserting one in your binary search tree. So after that, two is coming for the insertion. Okay, so this is not predefined sequence. Okay, it is coming dynamically. So
So,
every time, hmm,
so one more thing, you said balance. Let's say we take 3, 2, 1, we change the sequence. We just say first 3 elements, we change it 3, 2, 1. The rest 4, 5, 6 remains as it is. Then you'll also get a triangle, but again, it's only going on the left and right, and the middle is totally empty.
but this sequence is actually we don't know this sequence as a predefined. Okay.
I know, but we are again, just like here, we had a worst case. Even for balanced, right now it is totally unbalanced.
Hmm.
And if we go to balance, where the left tree is equal to right tree, if I change the sequence, I create a, synthetically create a worst case. If we say
Yes.
3, 2, 1, and
Hmm.
4, 5, 6, if you draw the BST,
Hmm.
it will also be balanced, yet not intuitively, it is not going to work well because we still have a lot of levels, right?
Yes.
Because
Yes. Yes.
the middle sections are not filled in, so we'll have inefficiency.
Dhananjay, oh sorry, can you mute yourself? Yeah. Okay.
So maybe it is a even number of elements. If we had like an
Hmm.
odd number of elements, like seven elements, it will be perfectly balanced. So it will be middle element 3 on the left and 3 on the right. We can always construct a worst case to counter that argument.
Yes, so this is also we cannot say the actual balanced. Okay, suppose we are creating like this, so still you are getting n by 2 height. Okay, so this is also not useful. Balanced means for the each node, the left subtree height and right subtree height should be approximately equal. Okay, so that means this.
Except maybe leaf level or
Leaf node is actually only the single node. There is no child after that.
right, okay.
Okay, so actually we want that our final binary search tree should look like full binary tree or heap. Okay, so you know the heap structure where we are filling all the elements level by level. So in that case, you are inserting maximum element and you are getting minimum height. Okay, so that is the case for the balance actually. So this is the next part of the binary search tree. We will learn in the big 7 actually. Before that, we will discuss some more things. So this is the insertion thing, searching thing. Okay, so that means algorithm we can create for the insertion. We will start comparison from the root node, and based on that we will insert. And same algorithm similar algorithm we can use for the searching. We will start comparison from the root node, and then based on the value and condition, we will just traverse accordingly. And similar for one thing, suppose if binary search tree is given. Okay, so let's see this example, first example. So binary search tree is given and we want to find out the maximum element in the binary search tree. So what process is required? So can you just see where the maximum element is coming in the all case?
Rightmost part.
Right side.
Yeah, correct. So we are just creating this binary search tree in that way. So we are already always adding the highest node on the right side of the current node after comparison. So definitely we will get the maximum of all the elements on the rightmost child. Okay, if we are just starting from this root node and just traverse on the right side until you are getting the right child. Okay, so you are getting right child 20, then you are getting right child 25, and there is no right child after that. So this is the maximum node. Okay, so if you want to find out the maximum node, just traverse the tree on the right side part. Okay, so this is the maximum. Similarly for the minimum. Okay, so for the minimum, Just traverse the any search tree on the left part. Okay, so last element, which is left child, is a smallest element in my research tree. Okay, so these operations you can perform if you know the if you have binary search tree, you can find maximum and minimum. And deletion operation. Okay, so what we actually just for the deletion per operation. So I'm just creating one example. So 20, 30, 10, 5, 15. So for the deletion operation, so for delete operation, we get three type of condition, three type of case. So what are the three type of case? Suppose we want to remove the element which is a leaf node. Okay, which is a leaf node. So leaf node we can directly remove. So suppose I want to remove this 5. So just we will move to the parent and we will just remove the reference of left child. Okay, and for 12, 17, so leaf node we can directly remove, or we can set the none value at this leaf node address on the parent address field. We can just change the address and we can remove simply. Another case is if we want to remove the element which have one child. Okay, so suppose case like this 50, and here this time we want to remove this 40 in binary search tree. So first step is we will find out this node. Okay, so 20 and 30 then 40. After finding out this, we will check so how many childs are there. Okay, so this have only one child. Okay, and one child or one subtree we can see that. So maybe there are another nodes which are connected uh, below 50. Okay, so we will just check that how many subtrees are connected. Okay, on right subtree or left subtree. So here you can see only one right subtree is connected below this 40. So to remove this, just move to the so just read the what is the address of the your of the right child. Okay, suppose address of right child is like R. Just maintain keep this R address which is already stored at the right field. Suppose if I'm creating the structure of this 40 node, so this will look like this 40 and right, we can see right address and left address. Okay, so we simply read the right address to identify this right subtree child, and we will store this right address on this right address of this 30. Okay, so 30 is also look like this 30 and right and left. So we will directly read the right address from the 40. Okay, and we will just store on the right address part of 30. So that means this link will be updated directly, and this 30 will directly connect it to the 50 subtree part on the right side. Okay, so this update is required for the deletion of one node which have one child. Okay, similar for the left child. Okay, we will read the left child node and we will just update the address in that way. But what happen if we want to remove the node which have both two child? Okay, so next case is like now we want to remove suppose this 20.
Sir, one question.
Mhm.
Suppose we are at 40. How can we go back to 30? Because uh, we
So
know
you
that.
can simply take two pointers. Okay, which so you have already performed some operation on the linked list. You can simply take two pointers when you are shift moving. Okay, so one pointer will keep as the previous node and one pointer will move to the current node. So every time just shift two pointer. Okay, so look like
Or can we just copy the whatever is there in 50 to 40 node? Uh,
okay, that you can also do. Okay, but 1 second. You want to copy that value, okay?
Whatever the value of this is to 40, and whatever the left and right.
But still you have to update something. Suppose some elements are connected like 45.
So whatever is the left part of 40, we connect to the left part of this.
So that thing you have to do many things. But when we are updating on only on 30, so we will only update the address like 250.
So we do
So
not have to update the other values,
Yeah,
right?
remaining part there is no required to update.
even in databases, let's say this is for one particular column, right? If that column is a foreign key for another table, so
Yeah, correct.
then it will create a integrity issue.
Yes.
So are there two Smiths?
Sorry, I'm using two devices.
Okay, fine.
Yeah.
Okay. So the next thing is if we want to remove the node which have both subtree. Okay, so left subtree or right subtree. So how we can perform this?
We'll have to recalculate using uh, the previous one. So if we are deleting 15, like
No, I am
I
talking
remember that.
about suppose if you want to remove 20 root node. So now root node have both 10 and 30, left subtree or right subtree. So what value we should replace by this 20? Here we cannot remove directly. Here we perform the swap operations by the value, and then we will remove the another elements.
Since the right side is bigger, it looks like the left child will get the promotion.
No, actually, so which element you will swap?
I don't know, sir. It looks like 10 because if I move 10,
Huh?
then the right side property will be preserved because one of the property of BST is all the right elements, right child has to be bigger. So that means if I promote the left child to take the parent's position, when I
Huh.
remove the
So
right, so that
yeah,
property will be preserved.
yeah. So right side property will be preserved. What about this 15, 17, which are coming on the right side of this 10?
Yeah, so that's a bouncer, sir. No
Um,
answer.
Yeah.
I have no
Okay.
idea.
So there are two things. One thing is if we found the successor, okay, successor of this 20 or predecessor of this 20. Okay, so we can choose any. Okay, successor of this 20, successor means in the terms of value. Okay, and predecessor in the terms of value. If we can find any, we can swap with it. Okay, so successor means just if we write the correct order in the sorting order. So what is the next value which are coming after the 20 in the increasing order?
25.
25. And what is the just smaller value which are coming before
17.
20? 17.
17.
Okay, so this 17 is actually
7.
predecessor, and this 25 is called the successor.
So programmatically, we have to traverse the left hand and go to the rightmost element, and on the right hand side, we have to get the leftmost element, something like that on the
Yes,
leaf,
yes, yes,
right?
correct.
Programmatically.
Yes,
Yeah.
yeah. So just to identify this successor or predecessor, suppose if we are selecting successor, just move to the right child and just after that, just try to identify the leftmost child. Okay, after reaching the right child, just try to identify the leftmost child.
Hmm.
If there is no part is connected on the left of this 30, suppose, so this 30 will become a successor. Okay, so you can identify in that way. So similar you can also perform with the predecessor things. So we will choose any one approach. So suppose we are selecting with the successor. So after finding the successor, just swap the value. Okay, so this 25 will come at this place and 20 will come at this place, and after that this will become a another case where the this node will have a zero child. Okay, so that means we have three cases: zero child, one child, and two child. So when we are performing this swapping operation in two child case, so it will automatically convert into a zero or one child case. So after swapping, just remove this element from the binary search tree with the previous simple approach. If you are have only zero child, then you can directly remove. If you have one child, just update the address Okay. So,
Again, apply the delete function on the right or left.
yes, after swapping, just perform the delete operation on that update swapping elements. Okay.
So
So,
just one thing, like I missed this. When you like, we are deleting 20, and then we are
so for 20 removing, just go to the parent node. Okay. So here there is some field. Okay. So one is value field and value is 30, and one is left child which contain the reference of left child, and one is the right child field which contain the reference of right child field. So just store the none value here if there is no child, okay, below this. So automatically this link will be removed and this no child will remain. Okay. So this is the way to remove the node which have zero child.
See, that is fine, but like
Hmm.
when we were deleting 20 and then we were saying that we'll have the highest, well, the nearest element on the right and the nearest element on the left, like 17 and 25 were there, right? So if we are removing 20, uh, how we are like doing that? Like we're replacing it with 25, but then how are we actually doing the replacement?
No, this is the procedure to identify the successor. Okay, so first
Okay.
step is uh, if just check that this which node we are removing have both child, left child or right child or not. Okay, if nodes have both child, you can simply identify this. Just check the left field or right field. If both are not null, that means this node have a both child. Okay, if you are finding this case, just apply the successor uh, operation on that. What is the successor of this 20? Okay, so successor operation will return the value or node position uh, of this 20. So suppose your successor operation is getting this 25 is the successor of this 20, then just simply swap the value. Okay, just copy the value 25 here and 20 here. Okay, and apply the delete operation on this node, successor
Okay,
position
okay,
node. Okay.
okay. Yes, sir.
So this operation we will perform for the deletion things. So these are the three cases will come when we are deleting
So
nodes.
ideally, which one we should do, the left one or the right one? Which
You can choose any. You can choose any predecessor or successor. You
standard
can choose.
practice?
Hmm. So both will be actually after performing this type of operation, your binary search tree will remain binary search tree. Okay.
Standard practice is doing what? I mean, left predecessor or successor?
You can select any.
Okay.
Okay.
Sir,
So there is no
intuitively,
foundation on this. Yeah, both are fine.
if we are maintaining the size of the left tree and right tree, we can actually to maintain the balance. Intuitively, it makes sense to replace with whatever will actually create less
So
imbalance.
actually, it will not affect this height things. Okay, suppose you can see what is the height of this left or what is the height of this right.
Yeah, it will not impact. No.
Okay, so if we are replacing with 17, still the height will remain the 3 or 4. Okay, and same for the right.
But in a large tree, when there is n, which is 2 to the power k, 1 will really not matter for that purpose, right?
Yes.
Yeah. So I think the whole idea of a predecessor or successor is it is basically going to be a leaf node, which will have no
Not
child
leaf
node.
node, not leaf node.
Oh yeah, it could be intermediate actually. Yeah.
Yes. Okay. So maybe this node contains some right node.
So when we swap, how does it get balanced? All that part is not clear.
So balance is not required for this deletion process. We are not performing balance operation here. Okay, so we are simply maintaining after performing deletion operation, our binary search tree should remain binary search tree. Okay, conditions should not be violated. Okay, so 30, 25.
So maybe take a difficult example and explain because the easy ones we get it. Like if you delete the root node and then replace it with a successor, which has both the nodes. So that's the most complex scenario.
Both the node condition is will never come for the successor or predecessor.
Okay, sir. Okay.
Okay, so if you are taking the both node of this, okay, well, sorry. Okay, so definitely this 25 will not be successor. Okay, successor will be this left row.
Its left child will be the successor. Yes.
Right. Makes sense
Okay,
because of the
one
BSP.
case can become if this 25 have the right child, like 28, it store the 28.
Yes, sir.
Okay,
Yeah.
and this is 20. So this type of condition may be come. So in this case, same things you will perform after finding the successor. So this is a successor, and swap the value. So 25 will come at the top,
And
and this will
28
be
you have to
20.
promote.
Yeah. So this now we will remove this 20. So now you can see this have only one child case. So this is coming as a one child case.
You have to
So in
promote
this,
28.
so 28 address will be stored on the left part of this 30.
Yeah. So that is the. So in other words, we have to take 20 whatever self dot next, whatever that, I mean, the dot head or whatever it is. If you are taking that, has to be updated to prev node.
Yes.
Yeah, it's quite
Okay. So similar for the predecessor things, you will always get the condition when the 17 or this predecessor node have only zero child or one child. In this case, you will always find the left child if you have this one child, not the right for the predecessor. Okay, so these are the possible case maybe come at the time of deletion process. Here we are not maintaining any height during this deletion process. Okay, so we will choose any one approach. Either we will find the successor or we will select the predecessor for replacement.
So
Okay,
this is the Hippify kind of equivalent, right? Because Hippify was doing that.
Heapify. This is not the Heap. Okay, so Heapify.
For Heap.
So for sorting process, actually we are using this Heapify process. Every time we select the maximum element and we replace by the last position, and then perform the Heapify operation. So you are talking about that?
Yes, sir. Last week, Bhaskar sir
Ha
was
ha.
that. Yeah.
Yes. So that max heap or min heap we can use for the sorting. So in that case, we perform this swapping things. Always we heapify the max heap, and we get the maximum element at the top, and we swap this maximum element at the last with the last element.
To find an element in a heap is very difficult, but to find an element in this kind of tree
So
is
this
easy.
type of comparison may also be asked in the exam. So suppose if you have max heap, so what is the time required to find any maximum? Sorry, maximum element. What is the time required? So you can say that the constant time. Okay, maximum element in max heap will always at the root node. Okay, so you can find in constant time. But what about the minimum element?
And okay, sorry. Yeah,
Order,
and order n.
order.
Huh. So you have to traverse all the element in the max heap, and then you can find the minimum element.
Because their order is not preserved for
Yes.
Heap, whereas here the order is preserved. So that's why,
Yes, correct. In heap, actually, we are maintaining only parents and child. The parent will be should be high compared to the child node.
The
But
minimum element will be in the last, in the leaf node only, no, sir? Minimum
leaf
element.
node, yes, correct. This is correct. But still, you have to traverse all the leaf. Na?
Okay.
You can not directly traverse the leaf. You have to coming from the root node, and then you have to
They
traverse
are
all
the
the leaf.
last. They are the last half, second half of the list, right?
But you cannot directly
N
move to
by two.
the
That is
second half.
that is n by two.
No, you cannot directly traverse the second half.
Sir, maybe a dumb question, but how is a min heap different from a sorted list?
Sorted list. So min heap is actually not the sorted order. Okay, if you
Okay.
draw the array, if you see the array of min heap, you will not get the sorted sequence.
it will be in the
Okay.
middle actually, right? The minimum element will be in the middle. Whereas in the
Okay.
sorted
Okay.
array,
Okay.
minimum
No,
will
no,
be at the
no,
front. Huh?
no. In the array, actually, we how we represent this heap actually in the array. We start from the traversing for suppose this is a heap. I'm creating min heap. So okay, 10 and this 20 and this like 15, like 40. Okay, 50. and 25 and 17 like this. Okay, so this is a main heap, one example. So if we just represent the array for this, so this is look like a 10, 20, 15, 40, 50, 25, 70. So in
Oh,
that
okay, okay.
verse, okay, like
So
level by
like
level.
we just look at the last four elements to find the max element, right?
But how you can directly? Okay, okay. So you are saying in this heap is represented, you can directly read the half element.
But that is also n by 2, so it is
Hmm.
the order of n only.
Order of n, yes, correct. Okay. So actually in heap there is no relation between left or right child. We are not maintaining any relation between left or right child, but we are maintaining the relation between parent or child only. But in binary search tree, we are also maintaining these things. Left side should be less than, or right side should be greater than. That means we are maintaining this three node property between all three nodes: parent, left child, and right child. We are all maintaining all the comparison. Okay. Because of that, we are getting one ordered, and we are using this benefits of this order.
So maybe out of syllabus. So if I have a database index, I'm searching, let's have a bank database, I'm searching for customers. So I'll kind of create a binary search tree because I can locate the customer quickly. But if I'm running a platform like Netflix and I want to recommend the best movie to a customer, so that means I have a probability vector and I have to keep the top three movies with the highest probability. So it is a priority queue. Every time the person watches, I keep updating, right? So it looks like it's like a priority based on priority. So depending on the application, would we change the data structure, or maybe it's too early? I'm trying to see like how would we apply in real life.
Real life, actually, in the database system, we use the different data structure that is called the B tree or B plus tree. So that is actually not in our course, and this is also similar to this binary search tree, but here actually we are storing one element at the each node. Okay, but in B tree or B plus tree, we store many multiple elements on each node, not a single element. So in B tree, actually, we also reduce the height in our data structure. So it look like this. We store many elements, or suppose I am creating three order binary tree. Okay, three order B tree. Sorry, B tree. So that means three order B tree means each node contains three elements or four child reference. Okay, like look like this. So here we can add so look like index things. Okay, so we can store elements like this, so 10, 30 and 50. So this node is containing three value, and in for three value this is also connect four child. Okay, and that node also contain three value. Okay.
So intuitively, if I got n, I was getting log n with base 2. In this case, it'll be base 3, right? So it'll be much faster.
Hmm. Yeah.
That's
So
the
here
good.
actually this is like index. So this first node which is connected before 10 will always contain the value which are smaller than 10. Okay, so 1, 5, 7 like this. Okay, so which node are connected between 10 and 30 will contain the value which are coming in this range. Okay, so 12, 40, 14 like this. Okay, so this first node is actually providing the indexing things, and when we are searching, so we will just first we will compare the value. If our value is available at this first node, okay, so if suppose we are searching 45, so for 45 we will compare with the first value, so which is greater than. Okay, now we will compare to the second value, which is greater than. Yes, now we will compare to the third value, so it is smaller than. Okay, so 45 is coming in this race, 30 and for 50. So now we will move to this child which are connected between this. Now we will search this. So B tree structure, it look like this, and generally in database we use this B tree or B plus tree. Okay, I'm not going in much deep, and this is also on another data structure. Oh, and the another scenario which you have mentioned for the Netflix and preference or priority things. Actually, we will discuss one topic in week 8. I think week 8. Okay, week 8. Yes, inversion pair. Yes. Huh. So there is one topic, inversion pair. We will just study in the week 8. That is actually used for the preference. So for this movie rating. Okay, so which OTT platform, which actually sometimes they suggest some things based on our searching. Okay, what we are searching on the on our OTT platforms, and based on that they also recommended some another movie which we maybe like. Okay, so one algorithm we will learn in the week 8, which actually helpful for this OTT recommendation. Okay, and that algorithm is actually called the inversion pair. Okay, so this is binary search tree, and these are some basic operation: insertion, searching, and deletion. Yeah. So suppose if our binary search tree is balanced, okay, so that means each node have both child like this, like this. Okay. So each operation we can perform in the log n time. Suppose we are performing insertion operation. So insertion we will simply compare from the root and we will insert at the correct empty positions. Okay, so that means we have to traverse the log n step for the insertion. Okay, and if we want to find any element, same things we have to traverse log n. We have to compare log n elements to find any elements. Same thing for the removing element. Okay, so remove element, if we want to remove any elements, maximum we have to traverse log n step to find successor or predecessor, and after that we will simply update the reference and then we can remove. So that means all operation can be performed in log n time if our tree is balanced. Okay, otherwise if our tree is not balanced and this is normal binary search tree, then worst case come in the pictures. So searching time worst case will be n. Okay, so similar, and the other operation also look like this. Okay, so this is the main things for the binary search tree. This is the main operation, and also traversing. There is one more operation, traversing operation. We have binary search tree and we want to traverse each element. So how we will perform this traversing operation in binary search tree? Okay, you have already seen traversing algorithm in the graph: PFS traversal, DFS traversal.
Similar to the birthday question that Sir was talking about in the video, birthday guessing.
Sorry, which
Birthday, like your birthdays are basically between 1st January to 31st, 0 to 365, and you guess less than greater than.
that one is the example of this binary search tree. That is actually binary search, not the binary search tree. Binary search example.
Correct, sir.
Okay.
So at each node, you recursively traverse the left child and then the right child.
Yeah, so there is one algorithm. There are three algorithms basically, and actually we will use some recursive approach. Okay, here we will start from the root node and we will traverse all the nodes. Okay, of this binary search tree. So there are actually three general way we used, recursive way we used. First is called the in order traversal. Second is called the pre-order traversal, and third one is called the post-order traversal. In-order traversal, pre-order traversal, and post-order traversal for binary search tree. And what steps are actually required for the in-order? First, there are very small change in the algorithm, and also code is also very small if we are using recursive approach. So for the in-order step, so I'm just simply writing the algorithm step. First step, first we will just use the base case. Okay, if our leaf no, so if left child and right child is empty, so there is nothing. Okay, so if so for the base case, so I'm writing the recursive main steps. Okay, base case we will create accordingly to stop the process. First step is actually recursive step, recursive call. Same thing. That means we are applying this in order algorithm on suppose R node. Okay, or we can say that n. N is called the current node. Okay, so in order algorithm we are applying on the current node n. The first step will be recursively call this in order on the n left child. Okay, first step is this. Okay, second step is simply print statement we can use, or we are traversing actually. Okay, so we can traverse, or we can print, or we can process some things in this step. So we are using print step, and we are simply printing n dot value. Okay, suppose I'm taking value for the current node. And third step is simply call this recursive algorithm same in order on the right child. Okay, so these are the three steps basically we'll perform to traverse in the in order traversal. Okay, that means first we will move to the left child, and then we will call the same algorithm on the left child. Okay, second step is when this step is completed, and we will perform the second step, which is actually printing the current node value. And third step is also a recursive step. We are simply moving to the right child of the current node and calling the same function on the right child. Okay, so base case we can make if our left child or right child is empty. Okay, then we will not call again any recursive call. Okay, so this is the steps you can just remember. So we can simply write this step in simple formula for in order. We can simply write left call. Okay, and n means print. Okay, so when I'm writing n, so that means this is the print statement, and r. Left call, right call, and print statement will come in between. Okay, for pre-order traversal, we will shift this print statement before l, and this L will come at the second step, and this right will come at the last step. Okay, just change the order. For the pre-order, just write this statement before in order, this first statement. Okay, so step will become first print the current node value, then move to the left child. Okay, this is recursive call, and move to the right child. Okay, and for post order, first step we will use the recursive call on the left child and right child, then we will print the node. Okay, so this is the sort you can remember. In the in order process, this print statement comes in between left and right. In the pre-order, this print statement come before this L and R steps, left recursive or R recursive call. And post order traversal, this print statement come after this left recursive or right recursive call. Okay, so now if suppose how that so now I'm simply taking one example, and I'll apply all three algorithms on the node. Okay, so suppose 10 5 10 5 this is 20 1 6 and 15 30. Okay, suppose this is a one binary search tree, and we want to traverse each node using a in order traversal. So in order, you just remember this left or print or right steps. Okay, when we will start these three steps on the root node, so left and r. Okay, so you know that when we are writing the code, first step is the left recursive call. Then that means we will move to the left node, left child node, and we will call the same algorithm on the left child node. Okay, that means these three steps we will perform on the left child once again. So this is the recursive nature. So I'm calling this recursive algorithms in this manner. So we are calling this L and R. So these are the three main steps. First step we will perform. Okay, so we will always perform the steps in the first, second, third. So first step is left recursive. So that means when this step is coming, we will move to the left child. Okay, so left child is exist. Okay, so this is we will move to the left child. Once again we are calling the same algorithm, so that means we are passing the left child node address of the same algorithm. So there are once again 3 steps are there. Okay, now current node is 5. So for current node 5, once again we will perform these 3 steps. So first step is left. Okay, so now we will move to the left child because left child is exist. Once again we are calling these 3 steps on left node. So one, this is one. Now current node is 1. Okay, now we will call this first step left child, but there is no left child. Okay, so this is now a base case. So in this case we will not do anything because there is no child available on the left side. Now we will perform the second step of this stage. So this is a print statement of current node. So what value will be print? One value will be print. Okay, now third step will be performed write recursive call, but write is also not there. Okay, so write, now all 3 steps are complete, and when all 3 steps are complete we will move back in the call. Okay, where we are coming from. So now first this L call is completed on the left side. Now second, what is the second step? Print
Nice.
statement. Okay, so print current node. What is the current node? 5. So second element will be print 5. Okay, now third step is write recursive call. Yes, write is there, so we will move to the right child. Now once again calling to the same algorithm on the right child, and R. Okay, now first step L, no child. Okay, so we will not do anything. Now second step is print the current node. So the current node is this 6. Now third is R recursive call. So R is also not there. So all 3 steps are complete. Our algorithm will move back. So the recursive call will move back to the previous call. So now our part is complete. All 3 steps are complete. Now this call will back to the previous call. So yeah, L part is done. Okay, so now we will move to the second step here, N. So N will be, and now current node N is 10. So this will be printed. Now R. Okay, so R means we will move to the right side. Now L and R. Okay, now first step is L. Yeah, L is there. Now move to the left side. So this is L and R. Left step is not no element. Now current node print 15. Okay, and right, no right. Okay, so all 3 steps complete. Move back, and L part is complete. Now second step is print statement. 20 will print, and now recursive call R. Move to the right side. Same step L and R. Okay, left is not there. N steps 30 will be print, and R steps. Okay, R is not there. Now all these 3 complete. Now this R complete, then R complete. All steps are complete. So you can see you are getting this order, printing order. So when you are applying this in order traversal on the binary search tree, you will always get the sorted order. Okay, you can see you are getting sorted order in increasing. So this is the way of the in order traversal. Here, this root node will always come in between. Okay, so we cannot simply, if suppose if this order is given to you, this is the in order of binary search tree, and binary search tree is not there provided to you. So you cannot identify what is the root node by looking this order. Okay, because the root node will always come in between, but we cannot identify what is the root node actually. So, okay, so you cannot create binary search tree, the same binary search tree, if you have this in order only sequence. Now second another traversing algorithm is this pre-order traversal. Okay, so same graph I will create now based on
No,
the
what did
step.
you say that we cannot use binary search tree and what in order or something?
So suppose this order is given, in order is given. Okay, this sequence is given, and this is mentioned that this is a in order of one binary search tree. So you cannot create the same binary search tree using this information. Okay, because you don't know what is the root node. Okay,
So this function is in a, there are multiple trees which can produce the same result.
yes, correct. Okay, so now apply the another algorithm, pre-order traversal, for the same graph. Okay, 10, 5, 1, 6, 20, 15, 30. Okay, now the second pre-order traversal, we use print statement first and left recursive call or right recursive call. This our order will be this for the algorithm. Okay, so this is pre-order traversal. So we will apply the same steps on the from the root node. So N, L, R. Okay, so now first statement is print statement. 10 will be printed. Now second statement is left recursive call. Okay, so that means we will move to the left child and we will call the same algorithm on the left child. So same steps, N, L, R. Okay, so first step is print statement, print current value, so 5. Now we will move to the next step, left recursive. Okay, we will move to the left side, N, L, R. Okay, now print statement current node 1. Okay, so now there is no left child, no right child, all three steps are complete. Now move back, and this left part is complete. Now next step is right call. Okay, so right is there, move to the right side, and same recursive algorithm we will apply on the right child. So now first step is print statement. So this is 6 will be printed. Now left, there is no left, no right, we'll move back, all three steps are complete of this 5. Now move back. Now this left part is completed. Now our right recursive. Okay, so we will move to the right side. So N, L, R. So first statement is print statement. So this is 20 will be printed. Now left call. Okay, so we'll apply here N, L, R. First print statement 15. Okay, left is not there, right is not there, all three complete. Now move back and right call. So right call is there. So N, L, R. So first step is print 30. And left is not there, right is not there, all completed. Now move back and move back. All steps are completed. Okay, in this recursive lecture. So you are getting this sequence. The algorithm is traversing each node in binary search tree, but now this time order is different. So this order is actually called the pre-order traversal. Okay, so this may not be any increasing or decreasing order. So this order may be different. So, but here this time we can identify the root node. If suppose this pre-order is given, you can identify the root node. But if this information is given, suppose this order is a pre-order of binary search tree. So in pre-order, root node will always come at the first position. Okay, because we are applying pre-order traversing from the root node, and first statement is the print statement. Okay, so that means this first node will always be the root node in the pre-order sequence. Okay, so we can identify the root node here this time. So pre-order is given, you can create a binary search tree. So here 10, you know this first node is a root node, you can create it 10. After that, simply applying the binary search tree insertion operation and insert the node. Okay, so you will insert 5. So 5 is smaller than this. Okay, so 5 will insert here. Then insert 1. So 1 is smaller than 10, and 5 you will insert 1 here. And 6 is smaller than 10, greater than 5. Okay, 6 will come here. 20 is greater than 15, greater than 10, smaller than 20 will come here. Okay, and 30 is smaller than 10, greater than 10, greater than 20, 30 will. So for this, if pre-order is given for binary search tree, you can create a binary search tree again, because this time you know what is the root node. Okay, clear? Similar for the post order traversal. So post order traversal, Okay, I'm creating once again. Okay, so 10, 5, 20, 1, 6, 15, 30. Okay, now post order. Post order steps are left call, right call, left child recursive call, right child recursive call, and then print statement. Okay, so if we apply this L R N, okay, first step is L, move to the left side. L R N. First step is left. Okay, move to the left. L R N. Okay, now there is no left, no right. Now the print statement. So first value will be print 1. Okay, now move to the back. Now first step is complete, second step will perform. Okay, so right call, move to the right. So LRN. Now this time left, there's no left, no right. Now print statement 6 will come. Okay, now all three steps are complete. Now move back. Now this R part is done. Now third step is print. So this 5 will come. Okay, move back, all three completed. Now this R part is coming, so we will move to the right. LRN. Okay, so first step is left, move back, left. LRN. Okay, so first step is left, no right, print statement. So 15 will come and move back. All three are done. Move back, now right step. Okay, so right is exist. So LRN. Left is not there, right is not there. Print statement. 30 will print and all three done. Now this third step is print statement 20 and this is done. Now move back and this is coming at the last step, print statement of 10. 10. So this order is actually called the post order traversal. Okay, so once again same things, this time you can also identify the root node, because in this procedure root node will be print at the last. So in this sequence last node will be identified as a root node. Okay, and if post order traversal is given, you can create binary search tree again. So simply you can select the last node as a root node and just create the binary search tree in that way, in the reverse order. Okay, from the last to first. So insert the 20, 20 will add here. Okay, then 30, 30 will come here. Then 15, so greater than 10, smaller than 20, 15 will add here. 5 will come here, and 6, sorry, 6 will come here, and 1 will insert here. Simply pick last element as a root node and then insert the element from the reverse side one by one. Okay, and you will get the same binary search tree.
So coming back to your question you asked, so if we know the sequence of nodes or vertices visited, can we reconstruct the tree, right? So let's say it was loaded in the memory and we shut down the machine, right? So we want to store it in some kind of a, let's say, CSV file, and then when we restart, we should read the CSV and construct the tree. Let's say that's the situation, because these are all in-memory objects. When we shut down the machine, it will all go away, right? So we want to
Yeah.
store that, right? So that means I
Yes.
have to store it in some kind of a physical data. Let it be CSV file, whatever, right? I just
Yeah, for backup purpose we can.
yeah.
Yes, correct.
Because I have spent so much of time to sort the data, uh, and now close the machine. And tomorrow when I start, of course, it will be from booting time with
Yes.
constant the index or whatever. Otherwise, I had to redo it again, right? That's a waste of time, right? So
Yeah.
let's say,
In general, where actually we store the data in permanent storage,
right.
but for backup process, yes, we can use this approach to recreate our data structure in the current.
Okay. Yeah.
Okay, so these are actually three way to traverse the binary search tree. Okay, in order, pre-order, and post-order. And so just remember that in order provide the increasing order sequence. Okay, so one question I am remembering right now. So one question is asked in the exam. So where the value is not given. Okay, alphabets are given in the binary search tree. Suppose like this A and B, like this. Okay, C or any random. Okay, so I'm just writing in that way, but any random. Okay, I like D, C, G, F, H, like this. Okay, so this type of question is asked that what is the next? What is the successor value of G? Okay, what is the successor value of G in the terms of value? So this type of question is asked in the previous term.
So ASCII code, right? G is H, right? And ASCII, because it's never stored as a G, it's stored as a
A.
binary of ASCII, right?
No, no. Actually, we are creating a binary search tree, but we are writing. Suppose these are the elements, these are the value. Okay, but we are not showing the value, actual value to you.
Is it greater than G and less than A?
Huh. Suppose this is a one binary search tree where the actual integer value are stored, but we hide that actually.
Okay, okay, got it, sir. Yeah,
Okay,
yeah.
yeah. Now we are asking that what is the successor value of G?
Be greater than G and less than A.
F, I think should be F.
Greater than G and less than A.
Greater than G?
And less than A.
No, no. I'm asking in terms of value.
Sir, F.
Why F?
A, it will be A.
When we were deleting the root node, we were
No,
going.
we are not deleting.
Sir, just when we were actually discussing that example, we
Haha.
were saying that the successor of A will be F and the predecessor will be G. Right?
No,
We will go
that is
right and
that
then
we are.
go to left most. And then we'll go left and then we'll go to the right most.
So your
Right?
this is actually a predecessor of A.
Yes, and F is the
Okay,
successor of A.
successor of A. Okay, that means order is coming like this: G A F.
Yes, sir.
Okay, but I am asking what is the successor of G? So
A.
successor of G is
A,
A.
A, correct.
Okay, okay,
Yeah,
okay.
yeah, yeah, yeah. Good one, sir.
Okay,
Yeah.
so this type of question is asked in the previous terms.
Sir,
Okay,
discuss such questions very freely, sir.
yeah. So
Uh,
so we can ask any type. We can select like C. What is the predecessor of this C, and what is the successor of this C? So like this, just you can use another approach. You can simply apply the in order traversal.
Sir, I know in the exam hall you'll, kind of mix it up, right? A followed by H followed by I, right?
Yes,
So,
yes.
yeah. So just to, mess with our mind a little further.
Mm.
Yeah.
So you can use simply in order traversal on this graph. Okay, just apply the in order traversal on this graph, and that order you will get in the increasing order. Okay, after getting the increasing order, you can simply tell that what is the successor or what is the predecessor of any characters. Okay, if I'm just in order to apply the in order traversal, so this is look like left like this. Now D will be print. Now move back. Okay, the left is completed. So sorry, L and R. Yeah, left. Okay, now B is print. Now G will print. Now then A will print. Now F will print, and C and H. So you will get this in order traversal when you apply the in order on this tree, binary search tree. Now after that you can simply tell that what is the predecessor of which node or what is the successor of which node. Okay, so suppose B, what is the successor of B? This is G, next node, because this sequence is actually in increasing order. So you can easily return the answer after traversing this order. Okay, so just remember these things, basic things. So this part is actually binary search tree. Now we have discussed the things of binary search tree, or some question is asked about this height. What is the maximum possible height? What is the minimum possible height? Like this type of questions. So suppose height is given. Okay, suppose height is given is h. Okay, and it is mentioned that one binary search tree is given for height h. Okay, what is the minimum nodes and what are the maximum possible nodes in the binary search tree? Okay, If we are talking about normal binary search tree, that means just you should understand that this is a not, this is not balanced. This may be not balanced.
Minimum is H.
H plus 1.
Minimum is H.
Maximum node or minimum node?
So
Minimum
Yeah.
minimum
is
is
H.
H plus 1.
Here there is one confusion actually. So sometimes in the some books we start we write like this. Okay,
Level 0
suppose
or level 1, right? The first
yes,
root node.
yes,
Yeah.
yeah. Suppose this is a first node. Okay, this is first node. So for this node, some books it is mentioned that the height is for this node is 0. Okay, and some books height is mentioned that for this height is 1.
So what is Corman, sir? Corman is our Bible.
So actually in we actually mention these things in our questions.
Okay.
So suppose if our tree is empty, then height is 0. Okay, so these things we generally mention with the question if we are asking this type of question. So we generally mention this. If our tree have only one node, the height is 1. So you can just change your formula which you have learned based on this.
So then the minimum node will be whatever H minus 1 and max will be 2 to the power H minus 1.
H. H.
Suppose I am taking height for the empty tree is 0. So that means one node height is 1. Okay, so in that case the formula will become changed. So like for the 2 height, the formula will be 2 to the power H minus 1.
Yeah.
Okay, so this is the formula. So in this case, if we are assuming this height, so what will be the minimum number of nodes will be H.
H. H.
Okay, and what will be the maximum? 2 to the
2
power
is to
H
the
minus 1. But suppose anywhere if you find these things, the height of empty tree is minus 1 and height of single node is 0. So accordingly change this formula. Okay, don't hard code read this. Like always just keep in your mind this is the edge, the formula of the height is this thing. Okay, so
That's
in some place you can find this another different
so the
information.
offset, basically, whether we call the root 0 or 1 level, right?
Yes.
Yeah.
So just change the formula. Now in this case, if you are assuming that the height of single node is 0, so you have to change the formula. So you have to add plus 1 here. Okay. Then in this case, this is the height 0 if the height of this tree is 1. Okay, so you have to add plus 1 here. 2 to the power H plus 1 0 plus, sorry, 1 plus 1 is 2, then minus 1 become 4 3. Okay, so accordingly change the formula based on the this initial information. Because I think if you have done the DBMS course, so if you have done, so in DBMS I think this single node height is mentioned as a 0 height in some place. So it may create a confusion. So because of that we mention these things in the question. So just read the initial case and change the formula accordingly. Okay, so these are very common questions generally asked. What is the height? If number of nodes are given, then what is the minimum height possible? What is the maximum height is possible for the binary search tree?
So, like, if the initial is 0, we go for 2 raised to power n plus 1
2
minus
to
1.
the power h. Agar, if height is given h,
Hmm.
okay, so we will add h plus 1. So
Okay.
you can see you have 3 elements. So for height 2, for
Hmm.
height 2, if you are taking height 2, you are getting 2 to the power h minus 1 equal to 3. Okay,
Okay.
here h equal to 2.
Hmm.
Okay, if height is mentioned for this is 1, then you have to change the formula. So 2 to the
Yeah.
power h plus 1 minus 1. Okay, so and then you are getting 3. Here h equal to 1.
Sir, we have done the recurrence. Now we are good at it. The
Hmm.
recurrence is about that, right? You expand and then once you see the pattern, then you create
Yes.
the formula. Same concept.
Okay, so this is the things of the binary search tree. Now comes on the next big 7 part. Okay, so big 7 is also start with the binary search tree topics, but this time actually what we are trying to do, we are just so this disadvantage, height is not the equal. This is our binary search tree is not the balanced binary search tree, so we cannot take the advantage of this. So how we can create the binary search tree, which will be the balanced binary search tree. So how, what procedure we can use to make our binary search tree balanced? Okay, at the time of creation. So we use actually one algorithm, AVL tree. AVL tree. Okay. So AVL tree have some basic condition and some rules at the time of creation of binary search tree. So what is the basic things? So for AVL tree, we use one balance factor. Okay, so balance factor we use, and what is the definition of balance factor is the left subtree height. Okay, so left subtree height minus right subtree height. Okay, the absolute value of this difference should be less than equal to 1. Okay, this is the valence factor we used in the AVL, and we calculate this valence factor for each node at the time of creation, and we check that what is the left subtree height and what is the right subtree height, and we just take the difference and take the absolute value, and that value should be less than equal to 1. Then we consider that our tree is, if each node maintaining this value. Okay, if each node maintaining this value in our binary search tree, then we just said that our tree is balanced. If this difference is coming greater than 1, okay, so like 2 3, if we are getting this difference is a 2 3 absolute value, so we just said that our tree is not balanced, and we apply some rotations on the tree, and we made the balanced. Okay, so first thing is to understand this balance factor things, how we calculate this balance factor. For some example, so insertion part at the time of creation of the binary search tree, so that operation is similar. Okay, binary search tree insertion operation, which we have already seen in the previous part. Same operation we will use for the insertion, but at the time of insertion, we will calculate this balance factor for each node. So suppose we have one a sequence, so like 1 2 3. Okay, or I'm just maintaining first balance thing. Okay, so like 3 2 5. Okay, suppose if I'm creating a binary search tree for this, so 3 first node we will insert 3, and it will become a root. Now if you check that what is the height of the left subtree, so there is no node, height is 0. Okay, left subtree height is 0. And what is the right subtree height? Subtree means which are connected below this left part.
0.
0. Right is also 0. So 0 minus 0, you are getting 0. So that means balance factor value for this node is 0. Then we will assume that this is balanced. Okay. Next step, when we are inserting 2. So we will insert in the similar way of the binary search. 2 is smaller than 3, we will insert here. Okay, 2 will come here. After insertion, once again we will check. Okay, what is the balance factor of 2? So balance factor of 2, what is the left subtree height? 0, right subtree height? 0. 0 minus 0, 0. Okay, now same things, balance factor for 3 we will calculate. What is the left subtree height? Now this time 1. Okay, so height means we are not counting the node, we are counting the height. Okay, so height we have already discussed in the previous example. Okay,
So height
just
is 1.
height is 1. Okay, for the left. What is the height of right subtree? 0 for 3. Okay, so just check for the 3. What is the height of right subtree of 3? So 0. 1 minus 0 is positive value. You are getting 1. So we are getting 1 for 3. Now you can see each node have balance factor which are lesser than or equal to 1. So there is no problem with this. That we will also assume that this is balanced according to our AVL condition. And next, if I'm adding 5, okay, so 3, 2, this is already, this is the existing minus 5 will insert here. Okay, now once again we will calculate the balance factor for each node. Okay, so 0, you know, left is 0, right is 0, 0 minus 0, 0. Now for uh, leaf node, so leaf node, you will always get the 0 balance factor, so there's no child on the leaf node. Okay, so 0 minus 0 for 5 is also 0. Now for 3, what is the balance factor? What is the height of left subtree? 1. Okay, what is the height of right subtree? 1. So 1 minus 1, you are getting 0. So these things you can say that this binary search tree is balanced. Okay, so there's no operation required to make this balance. Now suppose we take the different order. Okay, like this time 3, 2, 1. Okay, so first step is at the time of insertion first value 3. This will be become a root node and balance factor will be 0 because this is a leaf node. Okay, now we will insert the second node 3 and second node will insert on the left. Now the 2 is the leaf node, balance factor will be 0. And what will be the balance factor for 3? Left height is 1, right height is 0. So 1 minus 0, 1. Still there is no problem. Now when we insert 1, 3, 2, so 1 will insert because it is smaller than 3, smaller than 2, it will insert here. Now balance factor for 1 is 0 and balance factor for 2. So left subtree height is 1, right subtree height of 2 is 0. So 1 minus 0 is 1. Okay. Now what is the balance factor value for 3?
2.
Okay, so you can see the height of this tree is 2. Height of right subtree is 0. So 2 minus 0, you are getting 2. So now this is 2. At this time, you can see this is the violation of AVL condition. Balance factor you are getting greater than 1. Okay, so at any time when you are inserting a node, at any time if you are getting the balance factor value which is greater than 1 for any node, now you need to apply rotations on the current binary search tree to make this binary search tree as a balanced binary search tree. So these are the things. This is the first step. We will insert the node in the similar way of the binary search tree. After that, we will identify the balance factor for each node, and based on this value, if we are getting balance factor greater than 1 on any node, then we will apply the rotations. So what type of rotation we will apply? So there are 4 type of rotation we use. First rotation is called left rotation. Okay, I am writing short form, left rotation. Second is called left right rotation, and opposite side, third is called R rotation, right rotation, and fourth is called right left rotation. Okay, so these are actually 4 case, and based on this 4 case we apply the rotations. So first we will discuss LL rotations condition. Okay, LL rotation. So what type of case we apply the LL rotation? So suppose we are getting this type of sequence 3, 2, 1. Okay, so we are creating our any such tree look like this 2, 1. Okay, and balance factor we are getting 0 at 1, 1 at 2, at 2 here. Okay, so in this case you can see you are getting balance factor which is greater than 1 on 3. So this is the node where you are getting balance factor which is greater than 1. So from this node we will check which side the height is greater.
Left side.
Left side. Okay, just mention 1L because the from 3 left side height is greater. Now just move to the right, move to the child node of this 3, left on the left side child, okay, left child, and from left child just check that which side the height is greater.
Left again.
Left again, okay. So left again. So you are getting this type of sequence, left and left. So this is called the left LL rotation. Okay, this is the case of LL rotation. So if you are getting this type of situation, in this case, just make this position as a pivot position. Okay, okay, 3, and just apply the clockwise rotation. Yeah, Ritik? Huh. So just apply the clockwise rotation, and this 3 position will remain as a pivot position, and simply pull this 3 on the right side. Okay, so apply the rotation on the clockwise direction. So 2 will come at the 3 position, and 3 will become a right side, right child. So our structure will change like this. So 3, sorry, 2, 3, 3, and 1. Okay, so here this time we are applying rotation on this node.
How LL becomes right? Left seems like anti-clock. I don't know what is the
So
How
counter.
the addition happened?
this is the case actually for the identification what type of case we are getting, and
Hmm.
we will apply only one rotation which is clockwise, and
Okay,
we will
okay.
apply this rotation on the node which we are getting the higher value, higher balance factor value.
So
So
this is
that means
actually
three
a
will
right
be
rotation, right? This is like a right rotation.
Okay.
A right rotation, we can give any name, so we are simply saying that clockwise
So,
rotation.
okay. So
okay,
we
okay.
are having left. We are rotating it clockwise.
Yes, clockwise rotation. We are not giving some name for the rotations. Okay, condition we will check, we are getting L left condition, and based on that we will apply this clockwise rotation. So only one rotation we will apply, and we will simply shift one element in this way. Okay, so 3 will become right, and 2 will reach at the 3 position. So we will get this type of binary search tree. Okay, now you can see if you calculate the balance factor again, so you all are become 0, all are reducing actually. Okay, so main part we actually want to reduce this 2 value which is greater than 1. So this is now reduced. Now all the balance factor values coming, which are coming below than or equal to 1. So this is the one case. Okay, so rotation. Second, uh okay, so I'm just first telling the reverse case of this RR rotation. Okay, so third case, RR rotation. So RR rotation means, now if suppose we have one sequence like 3, uh, 3, 4 or 5 like this. Okay, so 3 will insert here. Okay, at the time of 3 there is no need to apply rotation. When we insert 4, still you are getting 0 valence factor on the 4 and 1 valence factor on the 3. There is no problem. But when we insert 5, so 5 will insert here. Okay, so now balance factor of 5 is 0, 1 on the 4, and 2 on the 3. Now this time, this is a just opposite condition of the LL. Okay, so we will check from the, so now this time this 3 is a node which have the higher balance factor. So we will check from this. So which side we have the greater height. Okay, so larger height. So right side. Okay, R. Now we will move to the right child, and then we will check which side we have the greater height. So right side. Okay, so R. So this is the RR condition, and in this case we apply the anti-clockwise rotation on this node 3. Okay, so this will become like 4 will reach at the third position, so 4 will come at here, and 3 will shift it here, and 5 will shift here. Okay, so this is the third case, RR type. Now come to the, so in these two cases we need to apply only one rotation. Now move to the next rotation, second rotation, LR condition. So when we get this LR type of condition, suppose we have sequence like 5 and 2 and 4, 3. Okay, so suppose if we create the binary search tree for this sequence, so 5 will insert here and 2 will insert on the left. Okay, if you calculate the balance factor, we will calculate after every insertion. Okay, balance factor for 2 is now 0 and 5 is 1, so there is no problem. So when we insert 3, so 3 is smaller than 5 but greater than 2, so 3 will insert on the right of 2. Now if you calculate the balance factor, so 3 is 0, this is 1. What is the balance factor for 5? What is the height of left subtree? 2. Okay, and what is the height of right subtree? 0. 2 minus 0 is 2. Okay, so you can see we are getting height which is greater than 2, greater than 1, sir. So in this case we are getting height which is greater than on this node, and this is a once again, yeah, we will check the case. So from this node we will check which side from 5 height is greater. Left side. Okay, move to the left child. Now which side height is greater from child? This is right. Okay, so we are getting this LR case. In this case we apply two rotation. First rotation we will apply on the child of the node which have the uh, greater than 1 balance factor. Okay, so this 5 node is actually have the balance factor 2. Okay, so which is violating. We will apply the first rotation on their left child. Okay, so this node, we will apply the first rotation on this node, and this rotation will be anti-clockwise. Okay, so we will fix the position of 2. We will shift 3 at the 2 position, and this 2 will become a left child of 3. So after one rotation, we will get this type of structure: 5 and 3 and 2. Okay, so this is the first rotation. I'm also mentioning one. And second rotation we will apply on the node which we are getting greater than 1 valence factor. So this is the second rotation we will apply on here. Now this is a clockwise rotation. Okay, so now this is the position, and we will shift 3 at the 5 position. Okay, so this will become 3 and 5 will shift here and 2 will shift here. Okay, so now you can see finally we are getting this after 2 rotation in this case. So we are getting 0, 0 and 0. Okay, so this is the case, LR case, left right. Just opposite case is RL.
So maybe 5 6 sorry, maybe 5 7 6.
576, yeah, I'm taking the example. Okay, so 4 RL case. Okay, so 5 7 6. So yes, so just opposite. So 5 will create, no problem. Okay, so 0 valence factor. When we insert 7, 7 will add on the right. So now valence factor for 7 is 0 and 5 is 1, no problem. Okay, so when we insert 6, 6 is greater than 5, is smaller than 7. Okay, so 6 will add here. Now the problem will come. So 0 and 1, and so here you can see the right subtree height is 0 and left subtree height is 2. So 0 minus 2, and we are taking absolute value 2. So we are getting valence factor 2 here. So this is the case. Now just check the case. What, so we are getting balance factor greater than 1 on this 5 node. From this node, which side height is greater? So this is right side. From the child node of this node, we will see which side height is greater. So left side. Okay, so this is RL case. Okay, so right is greater, left is greater. This case. In this case, once again we apply two rotations. First rotation we will apply on the child node. Okay, and this time this is a clockwise rotation. And so after applying this rotation, first rotation, we will get this type of 6 and 7 Okay, second rotation we will apply here on the 5, and this is the second rotation, and we will get anti-clockwise rotation. So 6 will come at the top, and 5 will become left, and 7 will become right. Now 0, 0, 0. Okay, so these are actually main 4 rotations. Actually, at the time of insertion, these 4 type of condition will come, and based on that condition, you have to apply the rotations. Okay, so for these type of rotations, some situation there is one more situation maybe occur, and what will be the situation? Okay, I'm just giving one example. So this is a simple example on 3 element. But what happen when we have more than 3 elements and we are getting one type of situation? Okay, so one another case. Okay, so I'm just first creating one example like 5. Okay, 3.
Sir, like in the
Hmm.
RL case, how did we like rotate it? Uh,
RL case,
hmm,
we are applying 2 rotation.
okay.
Okay, first rotation we are applying on the child. This is a clockwise rotation. Okay, we are fixing the position of 7, and we are simply shifting 6 at the 7 place, and 7 will become a right. So this is clockwise rotation. So we are getting the this one. Okay, after one rotation.
So like 5 stays where it is, and we swap 6 and 7.
No, no, not swap.
Oh,
This rotation will perform in the different way. So here actually we will shift this 6 element at the 7th position, and we will make the 7 as a right child of the 6.
okay.
Okay, this time we are actually performing not only swapping, we are also changing the assigning the children also. Okay, so initially 6 is a left child of 7. After rotation, 7 will become a right child of 6.
Hmm.
Okay, so for the rotations, logically I'm just explaining, but in the programmatically we will maintain these things.
So we can
Okay.
write
Rotation.
4 subroutines, rotation,
I'm,
LR, LL, everything. 4 subroutines have to be written.
now I'm able
Yes.
to get this. So I was not able to visualize before, but now I'm able to.
Okay.
Just looking at 6 and 7, if
Hmm.
I keep everything static and if I just rotate it clockwise, then we get this 5, 6, 7.
Hmm.
Okay, and if we just keep everything static, and then 5 and 6 if we select, and we rotate it anti-clockwise, we get this 5, 6, 7 final thing. Okay.
Okay.
And left is the natural way the clock moves, left to right, right? So it'll L means clockwise, R means anti-clockwise.
You can give this name. Otherwise,
Um,
by looking the structure, you can simply apply these rotations. If you are getting this RL or LR way, so just based on this logical structure, you can decide the rotations. Okay, so here actually clockwise rotation is required to maintain this. Okay, so just keep in your mind these things. So what two
so these are all
rotations we are actually applying when we are getting this situation?
these are things we have done in childhood, sir. When we are playing cricket or football, right? There's a natural
Yeah.
order of how good the people are, right? You go to play the game, you actually it's a AVL tree. We just didn't know that the team is trying to be balanced, right? So the next,
Yes, yes, correct. At the time of team decisions, player
yeah,
decision, player selections.
yeah.
Correct. Okay. So this is the normal case, and one another case I am just giving you. So just assume that we have one binary search tree at this stage. Okay. So if we find out the balance factor, so you can see 0 we are getting here. What is the balance factor of 2? This will be 1. Okay, what is the balance factor of 7? Will be 0. And what will be the balance factor of 5?
One.
1. Okay, so left subtree height is 2 and right is 1. 2 minus 1 is 1. So still this tree is balanced.
Balanced.
Okay, so we will not apply any rotations. So suppose if we will insert one more element, so that element I want to insert like, okay, one second. Okay, so for like 4, I'm inserting 4. Okay, so 4, if I'm inserting, so this 4 will be insert here. So 5, 7, and 2, and 3, and 4. Still this is not becoming a case. Okay, okay, so if we are inserting here, so the balance factor for this 4 is 0, 3 is 1, this is 2, this is 0, and this is also 2. Correct?
So we have two,
Shouldn't it be 3?
3 actually. Yes, 5 could be 3.
Okay, so in this case you can see we are getting two, means greater than one value at two nodes. So this is the chance you will get this type of situation. So in this case, always apply the rotations on the lower, which is coming first from the lower part. Okay, so from bottom. Okay, just apply the rotation on this lower part, this part.
Oh yeah, 2. It will only be 2.
Okay, so what type of case this is actually? This is a R. Okay, when you apply the rotation on this part, simply apply the rotation, just simply apply the anti-clockwise rotations, and 3 will come at the two positions, and you will get this situation. So 5, 7, and this 3 will come at this place, 2 will come here, 4 will come here. Okay, so I have simply applied the rotation on this part, and you can see after apply this rotations, the value which are coming above on the 5, 2, it will also reduce. Okay, so now this is 0, 0, 0, 0, and it will become a 1. So after applying a rotations on lower part, the upper part will also resolve. Okay.
Sir, in case of RR, we used to do 2 rotations, right?
No. RR rotation we only apply one rotation.
Oh, sorry. When it is LR or RL, we do like mixture of clockwise, anti-clockwise. But when it is of same, I guess LL or RR, then either we do one anti-clockwise for RR or otherwise one clockwise for LL.
Yes.
Okay, got it.
Okay, so this is the one thing. So lower part and upper part, if we are getting more than one node, okay, which have more than one value, so we will apply the rotations on lower part first, and upper will also resolve after rotation. So this is one thing. Another case is okay, one left child. Okay,
So
one second.
programmatically, how will you find here? Obviously, visual. How do you know whether we have to do 2 or so in the root node or
Actually, we always start things from the bottom side. Okay, so we always insert the node at the bottom. Okay,
right.
and at the time of insertion of bottom, we just apply the recursive process, and we just suppose I am inserting this 4 node at this position. So at the time of insertion, we will check what is the balance factor for this 4. Okay, so this 4 is 0, this is no problem. Okay, now we will move to the parent. We will move to the parent, and we will check what is the balance factor value for 3. So now this is 1, and okay, this is also okay. Now we will move to the next parent, 2. Now we will check the what is the balance factor for this 2, and at the time when we are getting this 2 value, we will apply the rotation.
Sir, in the last result, the balance factor of 3 should be 1.
This one, no, 0.
1
Oh
minus
yeah, okay, 0,
1
0.
minus 1.
Okay, so at the time of insertion, we traverse from the last insertion position to the parent root node. We will traverse in this path, and at the time of traversing, we calculate the balance factor, and at any time we are getting more than one factor value, we apply the rotations. So we definitely you will get the balance factor 2 value at this node first at the time of traversing. Okay, so you will apply the rotation on this part. After applying the rotation on this part, you will get this final tree, and then you will check the parent also after that. Okay, and then you can see you are getting 1.
So question is, so after any rotation, whether it is LR or RL or LL or whatever, right? So we are preserving the balance. So that means most of them will become zero, and the root will be whatever at max one. What about other intermediate nodes? I know you were showing two levels. If it is three or four,
Still, the balance factor actually we are calculating for the each node. So balance
right,
difference will be maximum one in the left
maximum.
subtree or right subtree.
Right, right.
Okay,
Okay.
so our tree will approx balanced, not the exact, but approx balanced. Difference will cannot be greater than one
So
between
that means
any
there can
sub.
be what is a max? So if I add up, sum up all the balance factors across all nodes, so what is the maximum value
So
in
actually,
a
that is not affecting anything. That relation actually we also not checked.
is there a theoretical upper bound? Anyway, we'll
Uh-huh.
code it and see when we do
Yes.
it. There has to be something, right? Because for a balance tree, at max, half of the things or less than that has to be, one. So it should be upper bound should be n by two. Intuitively looks
Yes,
like.
yes, yes, correct. Okay, so this is the procedure to check. Okay, so after inserting the element, we traverse the path from inserting position to the parent node. Okay, and we will check the balance factor on each node. At any time we are getting more than one, we apply the rotation. So definitely you will get the lower part which have the greater than one value first, and then you will apply the rotations.
So in this left diagram, instead of 7, suppose we have 1 here, left of 2. Left of 2 we have 1.
Okay, one.
And remove the 7, sir.
So this type of situation cannot be come actually directly.
Remove the 7, sir. Remove the 7.
Remove the seven. Okay, you are saying this?
Now, sir, 5 is unbalanced, right?
No, no. Actually, when we are inserting one by one, so this type of situation cannot come directly. Okay, so suppose uh, at the time, so after insertion this five. Okay, so five then two. So what is the third element you inserted?
Okay, either 3 or 1.
Three or one. So any element you are inserted at the time rotation will apply.
Okay, so the rotation has to come after every insertion.
Yes,
Like if
after
you,
every insertion, we check these things, valence factor for each node, from insertion position to the parent node. And if we are getting greater than one value, we are applying the rotations.
but
So,
suppose we have a unbalanced tree right from the beginning, sir. If you have a totally unbalanced tree right from the beginning, is there a way to convert it into a balanced tree, or we have to do it after every insertion only?
yes, you can perform this AVL steps from the bottom to upside. Okay, just traverse the, just apply any in order traversal or this type of algorithm, and at the time at the from the bottom side, just check the balance factor and apply the rotations. At any time you are getting any balance factor which is greater than one, you can apply the rotations. Okay, so in that way you can apply some algorithms that make can make the balance vernissage tree. Okay, but this for the AVL tree actually we are applying the rotation at the time of creation of vernissage tree. So after every insertion we apply, check these things.
Okay.
Okay, one more condition actually we have.
So, sir, like, so when we are going through the tree, as and when the balance factor it goes above one, we apply rotation.
Yes. Okay, so at position we will check this balance factor from the insertion position to the parent position. Okay, so there is no need to check balance factor for each node after insertion. Okay, so in this example, okay, I'm taking another example because height is only affected on that side which we are inserting the new node. Okay, so I'm taking one another example. There is one more case. So like 10, 20, 5, like say 8, and this is 4. So this is okay. There's no balance problem in this tree. Okay.
Balance.
And hmm, okay. So suppose now next inserted element. Okay. So balance factor, if we check this 0, 0, 0, 0, and 1. Okay. There is no problem. Suppose I inserted 1 in this. So you will get this 10, 20, and 5, 8, and 4, and this 1 will be inserted here. Okay. Now just check the balance factor from the last position. Okay, so actually we always check the balance factor from the last inserted position to the root position, because the right part is actually not after inserting on the left side, right side part balance factor is not affecting. Okay, so there is no need to check for the right part and all the things. Just check for the this path. So 0, okay, and 4 for 4 it is 1. For 8 is 0, the 20 is 0. So we will check for the 5. Now
One.
5 will become
One.
1. Okay, so 2 minus 1 is 1. Okay, there's no problem. And for 10, so 3 minus 1,
Two.
2. Okay, now can you tell me what type of case this is? So we are getting this time balance factor only
Left.
this node.
LR. LR.
No.
LL.
L. Okay, so which side the height is higher? From 10, left side. Now check from the 5. So which side height is greater? Left. Okay,
And
left side. So left side. So this is the case of the left, or and then we apply the rotation on this node, which is clockwise rotation. Now in this case, when we apply this rotation, so this 5 will come at the root position. Okay, correct? Then where this 8 will be shifted? Because
Right.
so if I'm applying only simple rotations, so 1 second. So just apply the
Left
one.
node of 10.
8 will
Then
become
10.
child of 10.
I'm first applying the simple rotation. I'm just shifting 5 at this root position. Okay, so this 10 will become on the right. Okay, and 20 will add here, and the left part of this 5 will remain as this 4 and 1. Okay, so now there is no position available for this 8. So because the 5 right child is already occupied by 10, left child is occupied by 4. So where we shift this 8?
left of 10. Left of 10, of course, we know which is left of 10.
Yes, correct. So this is also one another case that will come. Actually, when our current node is shifting at the root node, which have already 2 child, left or right child. So in that case, if we have right child of this current node, that will be make as a left child of the current root node. Okay, so 8 will be shifted here. Okay, now you can see our tree is managing the property of any such tree, and it is also a balanced. Now you can see after rotation this will become a balance 1 and 0.
So programmatically, this is the toughest one, LL. When you rotate, you have a LL situation and you are rotating the root node. This is the most disruptive.
Yeah, so this type of actually part you have to check. If the left child, if we are applying this clockwise rotation in this case, if and our left child is also containing the right subtree, so that right subtree should be connect to the current parent node left child, the left child position. So that things we need to maintain at the time of rotations. Okay, so similar case can be come in the reverse direction. Okay, so in the reverse diagram. Okay, like the opposite side. Okay, suppose we have this type of situation, 20 and 10, sorry, 15 and 30, and this side is 5, and we are inserting one more like 40.
Sir, why don't you put one between 10 to 20, let's say 17?
Where?
Oh, sorry, so we can.
Say in
Sorry,
the above,
Mhm.
so in this above one which you in which you rotated, and then five
yeah,
in the pivot one. Why is it not one?
Where you are talking?
So like is five cube per zero है, क्यों है?
Uh-huh. Here, five. This one.
Yes.
Yeah. What is the height of this part?
2 minus 2.
Okay, two. What is the height of this subtree?
Okay, two.
Height. Okay, so height we are not counting the node. This is also one very confusing problem. Some
Okay.
maybe mistake by anyone.
Is
Okay,
it
height.
one?
Okay, no height. Height of this. What is the height of this? Two.
Okay.
Okay, height actually we calculate. Okay, I'm also telling the idea. So suppose we have this tree. Okay, like this. What is the height of this? Complete.
1, 2, 3,
Four, four,
4, 4.
four, four.
Complete.
Five.
Okay. If
Sir,
we considering the number of
Complete,
nodes in the path.
complete will be four or I don't know, five or
Five.
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 if you're
Okay.
considering root to be 1, then
Longest path. Root to longest
Longest
path.
path, longest
Yes.
path is five.
Yeah. Okay. So we just check the longest path from root to leaf node. So just we check what is the leaf node. So we have many leaf node in this tree. So what is the longest path? So longest path is only this one. Okay. And in this path, how many nodes are coming? Five. So this is called as a height of this complete. Okay, so now in this example, if you see the this is the root node. Okay, we are calculating the height of this subtree. So what is the longest path? We have two paths and both have the same length. So we can choose any. So what is the height of this is 2.
Okay, sir.
Okay, and we are getting 2 height from the left, 2 height from the right. 2 minus 2 is 0. Okay, so this
Yes.
is the thing. Okay, so I'm just explaining the reverse situation of this child shifting. So this is the case of R. Okay, we are inserting last node here. Okay, before that it was balanced. So if we are getting this situation, we will are getting 0, 1, 0, 1, 2, 0. This balance. Okay, so this is the main node which we are getting two balance. So we will apply the anti-clockwise rotations on this 10. Okay, so now this 20 will shift at the root node, 30 will come here, 40 will come here, and 10 will come here, and this 5 will come here. So 15, where will this 15 will be added? 15 will be added.
to the right side of.
Okay, so these are the cases which will be come during the process. All I have explained all the cases which will become during the insertion of AVL tree. Okay, so this after understanding all these rotations, just look the implementation part. You will get the same type of things in the implementation. Okay, so we are simply getting the height, and we are comparing the height of left hand and right hand based on the value of the difference. We are just assuming which side height is greater. So you will get the same concept in the implementation. Just look the implementation after. First try to create some AVL tree on the paper and pen, using the on the paper by the pen. Okay, you can take any sequence. You can just randomly take any sequence and create the AVL tree, and just keep this rotations in your mind and apply the rotation manually. Okay,
To
because
check, so to check if the tree is correct, we do in place traversal, in order traversal.
yes, yeah, so definitely your output tree should be a binary search tree,
Right.
or and
And
the each
then
node balance factor should be a smaller than or equal to 1
if
in the
I do
pen.
a in order traversal,
In
then
order traversal, you will get definitely
the
sorting
sorted
order,
sequence of the
sorted
values.
sequence. Yes,
Otherwise,
yes, correct.
If it is not, if I've done any mistake, then I will know that my operations has not happened properly.
Also, the height, this balance factor should, balance factor values for each node should be smaller than or equal to 1 in your final result.
Yeah, yeah, that's also correct. Yeah.
Okay, so just select any sequence, any random sequence, and try to create ABL tree. Okay, so suppose I am taking any random sequence, so any one situation will come at the each time, and then apply the rotations based accordingly. Okay, so suppose I'm taking like 5, 3, 1, 8, 4, 2, 9, 6, like this. Okay, and once again or 10. Okay, so I'm just writing this, and after that I'll create one research tree. 5, no problem. 3 will insert, still no problem. 0 and 1. Okay, now 1 we will insert. So this is the case of LL. So after that, I will apply one clockwise rotation. So we will get 3, 5, and 1. Okay. Now I have inserted till here. So after applying the rotation, we are getting balanced. Once again, we will insert the new element in the balanced. Okay. So 8 we will insert the here. So 8 is greater than 3, greater than 5. Okay. So this is 5 greater than. Okay. So we will insert 8 here. So after inserting this 8, we will check balance factor value 0. Okay, so this is 0, 0, 1, and 1. No problem. Then we will insert 4. Okay, so 4 will be insert like
The
3,
five, left of five.
5, and 4, and 8, and 1. Okay, still you can see 0, 0, 0, 0, and 1. No problem. Okay, now we will insert 2. So 2 will be insert on the right of 1. Okay, so 3, 5, 8, 4, 1, and 2. Now you can see 0, 0, 0, 0, 1, 0. Okay, no problem. Now insertion of 9. So 9 insertion, 9 will be insert like this: 3, 1, 2, and 5, 8, and 9, and this will be 4.
Problem.
Still, I think
No,
there is no issue.
no issue.
0, 0, 0, 1,
3 minus 2.
1,
Yeah, 3 minus 2
1,
is 1
1. Yeah, still no issue.
problem. Yeah.
Now 6. So once again 3,
So there will be no
5,
problem.
still no problem. So my random input is actually not good.
Uh, you have a balanced mind.
Yeah,
Balance.
4, and 6 will come. 3 greater than 5 greater than 8. Sorry, yeah, 6 will come here.
So 10 will create problem now.
Okay, yeah, 10 will create a problem, and we will get what, critical diagram. Okay, so at the time of insertion, okay, so I'm adding here. Okay, so 10 when we are adding here. Okay, so now you can see we are getting 0 and 1, 0, 0, 0, or leave 0. So now 8 is 1, 5 is 2, correct, and 3 is also 4 and minus 2, 2. This is 1. Okay, so this is the unbalanced now.
So it will fall under RR.
So what value we are getting to from the bottom part? So this is 5. Okay, so this is coming as a R situation, or from the right child R side. Okay, so we will apply the rotation on this 5, which is anti-clockwise. So 3 will remain same, 1 and 2. Okay, now this 5, 8 will shift at the 5 position, and 5 will move here, and 4, and 9, and 10. Okay, and this 6 which is connected at the left of 8 will be shifted on the right of 5. Okay, now you can see 0, 0, 0, 0, 1, 0, 0, 1, and this is 1, 3, and 1, 2, 1. All are smaller than or equal to 1. So these two actually in this process we got only two case, unbalanced case, and we apply the rotations. So just take any random input and apply the rotation and check what final output you are getting.
These are quiz to questions. How many times you'll rotate the tree?
Yeah, this type of question is also.
This is like, definite quiz to question.
Yes, and also some basic input sequence is given, and generally ask that what is the sum of leaf node after the final output.
Yeah, you'll have distinct elements, so your sum
Yeah.
is only one unique answer.
Yes, so we just give the one small sequence only for 5-6 element, and just ask that create the AVL tree, and after that just return the sum of a leaf node. Okay, so this type of question is asked in the previous terms. Okay, so this is the way to create the AVL tree, and this is a balance. And after creating the tree in that way, you will get approx log n height. Okay, so then you can get the benefits of the binary search tree, search operation, insert operation, delete operation. You can all perform in the efficient way in the log n time. I hope it is clear to everyone. Initially, this rotation part is not actually, you cannot remember easily. So because of that, I am saying that just take some example and just solve 5 or 6 problem on the paper and pen, using the pen, and just apply each rotations. Then you will get idea totally. You will get understand what is happening in the rotations. Okay, and after that, just look the implementation. Then implementation you will find at the EG after getting these all concepts in your mind. Okay, so this is the AVL part of the research tree. Okay. Yes, so big 7 AVL part is done. Some basic property also keep in your mind. What is the maximum height or maximum number of nodes? So same things for the given height is actually the same binary search formula you can use. Okay, so maximum number are possible for the height is 2 to the power h minus 1. Okay, so if your tree is full, level wise full. Okay, but for the minimum case, actually sir is explained this formula uh, to identify the minimum number of node if height is given. Okay, so but initial case you should you cannot directly calculate, but you can calculate in the sequence way. So for the minimum nodes, okay, so this question is also asked many times in the previous term. So height is given like h equal to 5. Okay, so what is the minimum number of nodes possible in the AVL tree? So in this case, if we take h equal to 0, so our node number of nodes will be 0. Minimum number of nodes will be 0. Okay, when we takes h equal to 1, 0 height, okay, 0 and 1 nodes. Yeah, so for 1 we are getting so 0 case is empty node, 1 case we have only 1 root node. Okay, so like this 1 node, so 1, only 1 minimum node possible. Okay, after that for h2 you can simply get this information by just adding the previous 2 value and plus 1. Okay, so h0 plus h1 and plus 1, and then you will get the number of minimum number of node possible for height 2. So you are getting 2 here. Okay,
Like a Fibonacci plus 1.
yes, the correct one. Okay, so this time for empty, so this is the 0 for, okay, so the 0 for empty and 1 for single node. Okay, when we create the height of 2, okay, so that should be at least this one. Okay, so this like this. Okay, this is balanced. Okay, and here you can see the we are getting 2 nodes in, and height is 2. This is the minimum possibility for height 2. Okay, and when we calculate h3, so we will add 1 plus 2 plus 1. Okay, so 1 plus 2 plus 1. Okay, so h1 plus h2 plus 1. So this is 4. So this is the case when we add height 1 node. Okay, so height 1 is 0. And what is the height 2 is this one. Okay, so this one. Okay, so if we add both, we combine the both, so we will get like this. Uh, like this one. Okay, so we have added one part of the height and we have added this part, so this is actually h2 and this is h0, and we are simply combining by these by one node, so one is coming from here. And now you can see height is of this is 3 and this is also balanced according to the AVL. So we are getting 4. So you cannot directly calculate the minimum number of h5, so you have to come through this sequence, and after that after h3 there h4 is 2 plus 4 plus 1 is 7.
One minor thing on the right hand side, you wrote H0. That should be H1, right? H2 and H1 on the right. Because H0 is
Sorry,
empty.
1, yes, yes,
Yeah,
1.
yeah. Just to make sure we understand it. Yeah. Okay,
Yes,
thanks.
correct. Okay, so for h4 we have added h2 and h3 and then plus 1. Okay, so we are getting 7. Now for h5 we will get h3 is 4, 4 plus h4 7 plus 1, then 11. So this 11 will be the answer for h5 height.
12, sir.
Okay,
12.
so these small formula you can remember for this. Okay, this one. Okay. Huh. So this implementation is given AVL. Just look this implementation after solving some example. Okay, then you can easily understand this. After that, the one new topic is started in the week 7 is greedy algorithms. Okay. So greedy algorithm, as per the name of greedy. Okay, so this is greedy approach. Every time in this approach, we always take the greedy selections in the each steps to make the local solution optimum.
Okay, so that optimal substructure condition will apply on all these.
You can see. So you have already seen this Diasta algorithm. Okay, so in each step we select the node which have the smallest height from source. Sorry, smallest distance from the source. Okay, so we select that node. So that means from the local steps we are choosing this greedy selections, smallest height, smallest distance. Sorry. Okay, and based on this smallest local greedy selections, we get the overall optimum solution. Okay, so need to make a sequence of choice to achieve a global optimum. Okay, so some sequence is required, local sequence is required to achieve the global optimum, and each local steps we select the choice based on the greedy things, and finally we get the global optimum solution. And we never go back and revise an earlier decision. Okay, so same thing, the data is the best example for this. So if we have selected any node for the further process, then we never check the we never update that distance, we never check that node again which we have already traversed. Okay, that means we never change the decision which we have already taken before. So this is the things, drastically reduce space to search for the solution. Definitely we are solving the local problems and we are not looking the previous problems again, then we are reducing the problem size. Okay, and finally with this greedy strategy, yeah, okay, so this greedy is actually sometimes this greedy solution looks correct but not the always this is provide the optimum solution. Okay, so some proof is required for the optimality. We need to check our solution is providing the correct solution for each situation or not. So this things is required for the greedy. Okay, so I'll just explain, give some example after discussing some problems. Where initial times we looks that greedy approach will work, but maybe that will not work. So some example is given. You can see the dashed algorithm. We are using this greedy approach, prims, Pascal. So prims or Pascal, we also choose the smallest edge or distance, edge distance first. Okay, so now this interval scheduling, minimum lateness, and Huffman coding. These are the three topics which is discussed in the big seven. Okay, and all three are the example of greedy approach. First example is interval scheduling. Yeah, so these topics are very important for the quiz too. Some definitely one question will come from this interval scheduling or Huffman, and that question will come simple to check the concept. Okay, not any programming things or some situation is given, then just identify that what is the answer like this. Okay. So one scenario is mentioned in this interval scheduling. One IIT Madras has a special video classroom and delivering online lectures. Different teachers want to book the classroom. Slots may overlap, so we cannot assign the slots for everyone. Okay, because every teacher maybe ask for one particular slot. Okay, so we cannot assign to everyone, but here we want to maximize the allotment. How we can assign the maximum slot to the teachers. Okay, so where there is no overlapping happening, but how we can assign maximize our slot or allocation. So these type of problems. So one example I think is mentioned. Yeah, this type of question is generally asked. So one start time is given. So that means these are the A, B, C, D are the some activity or some teacher from the previous example, and they wants a slot where the start time is one and finish time is two. Okay, so that means they are just giving one preference where the start time should be one and finish time is the two, and we have many requests A, B, C, D, E, F, G, H. Okay, so this start time and finish time range maybe overlap with another. So these are the only request first. Okay, and based on this request, now our purpose we want to maximize the allocations here. Okay, so how we can achieve the solution for this? Okay, so how we can just allocate the slots in that way, so the maximum allotment we can done. Yeah.
So we can find the duration of the activity by subtracting start time from the finish time. So that will give us the duration, and that's like a edge, right? No, not edge, like
So
and
mine's
then
a Gantt chart.
yeah, well,
Okay, I'm just copying. Okay, so I can write here. Yeah.
so
So
if there
you
is
are
a
saying
overlap,
that you are calculating the difference of each slot. Then how you can identify that which slot should be
so greedy
allocated?
means our algorithm is greedy, right? So we want to make sure we give a slot to maximum number of activities,
Hmm.
right? So if I give the last slot to the activity with the lowest duration, that will be, so it could be anything between A to H. So if we do that, 2 minus 1, 4 minus 3, blah blah blah, right? So okay, the lowest is 1, so A is 1, then E is 1, and that's it, A or E, right?
Hmm.
And then I have to check if they are overlapping or not, right? So this is 1 to 2 and this is 4 to 5, perfect. So then we can assign A and E, right? So that means our slot is blocked now, 1 to 2 and 4 to 5, the room is booked. Now I have to find what are the lowest duration of the activity, and it should not overlap with the allotted slots for the allotted activities. No overlap, and then kind of go backwards, whatever is available. And then in a greedy way, I kind of start searching for activity with the lowest duration, and it also should be available. The slot should be available to be allotted. So maybe, I don't know, I'm just intuitively thinking
Yeah.
that
Okay.
is how it should be done.
Yeah.
Like one to
So
3 to 4, 5, 4 to 5, all these activities can be done.
so simply I'm just calculating the difference. Okay, so this is one, this is one, this is six. Okay, this is 3, this is 1, this is 4, this is 2, this is 2. Okay, this is the first step you are saying that. Okay, and after that you are selecting the activity based on the duration, which have the smallest duration. Correct?
Yes, sir.
Okay, so the first activity is A, and then B, then E you will choose.
And it is possible that these three could be overlap. In this case, there is not overlap because 1 to 2, 3 to 4, and 4 to 5, right? They are not overlapping. It's just we are lucky. Otherwise, there may be a chance that these three overlap, or it could be A could be partially overlapping and C could be partially overlapping B, right? So the next step would be to ensure we get. I mean, I guess we can always pick the first one. Uh, but within these three or whatever it is, like here we're getting three,
We can we
right?
can look close by, like C is 0 to 6, so that is overlapping.
No, so if we give 0 to 6, we consume a lot of resource, right? Because looks like we can schedule our sessions between, whatever, 1 p.m. to 10 p.m., something like that, right? So, so if we allocate a task C, means C class is a very long PDSA class, which will take 6 hours. So no other subject will get a chance.
Okay.
Yeah, I mean, I don't know. The greedy should be not allocating slot to activity which consume most resource, because
Yeah,
then we
this
are
is also a greedy approach. You are selecting you are calculating the difference and waste. You are selecting the smallest one first,
yeah,
and so this is also a greedy approach. Correct.
yeah,
And but you have to check this overlapping things.
yeah,
Okay, after selection you have to check this overlapping, and
yes.
still how you are ensure that in this way you will get the global optimum solution.
So there is no guarantee, sir, because I could locally get greedy, and then there is a lot of overlap, but then some slots could not leave open because, yeah, so it will not guarantee
Yeah,
global
so
optimum.
there are many way to solve try to solve this problem. So some another greedy approach maybe also come in your mind. So what is
So
the
can we
correct
take this as edges and the difference as weight and solve? Like
difference and weights means?
start and finish time is 2 nodes and the difference as a weight.
Difference as the weight.
We can
So
also
same things you are this is saying. So this difference we have calculated now.
yes, like I
So
just gave
based on that we are simply. So
yeah,
you are saying that you are creating graph from this.
yes, something like that I thought.
So sir actually talked about in a video lecture. So if we take these activities as vertex, right,
Yeah.
and we create an edge if the activities time overlap, then we draw an edge, otherwise not. Like for example, A is a vertex and its start and end time is 1 to 2. And if any of the nodes overlap between 1 to 2, then I draw an edge from A to that vertex. So here I see 1 to 4 is overlapping, like A to D will be a edge, and that's it. A will be connected to D, right? And B is 3 to 4, and there is nothing overlapping. So B will be independent. C is 0 to 6. So C will be connected with a lot of people because 0 to 6 is a very wide interval. So it will
No,
be
even
connected
if
with,
it's not connected, the weight is more, so it will not have preference.
I mean,
Not
yeah.
way. Right?
So it
Anyway,
is,
it
it
doesn't
is,
have any
what do you call
preference.
it, undirected weighted graph, basically, right?
Yeah, that is what it came to my mind.
Okay, so what difference for you are selecting the edge based on the difference now?
Correct. So then we have
Yeah,
these,
the weight will be the difference.
Okay, so one, two, two like this. This is one difference, and this is for A. And after that, when you are selecting the different one, okay, so 3 to 4. So 3 to 4 will come as a separate. This is one, and this is for B. So in that way, you are creating like this, no?
Yes, sir, I think there is some connection problem in between, right?
So 1, 4 to 5, you can choose because this
Yeah, four
ending.
to five,
Yes, you can choose.
5 to 9 will go.
Okay, this way. Now when you select this next greater value, so 2, okay, so this 2, 9 to 11, yes, 9 to 11 you can select like this separately, and 8 to 10 you cannot select because it is overlapping, correct?
Yes, sir.
Okay. So we got total 4 till now, and after that we will select this 1 to 4. Okay, so 1 to 4 we can also not select, which is also overlapping. So this is also crossed.
There are many approaches. I can say the
Huh.
time also 1 to 2. So I can, because my time starts with 1. So start with the start time plus whatever is the task or activity takes the least amount of time. So if I start with a 1, because I want to make the maximum utilization of the
So
resource
why
according
is
to
1 to 4 overlapping?
1 to 4, 1 to 2 overlapping. Yes. So if you
Okay.
allocate to A, D will not be
So
allocated.
1 to 4 is already overlapping, na? So with the 1, 2,
Okay,
and
okay,
3 to
okay.
4, it is
Yes.
overlapping. So we will not choose. And then 4, 5 to 9. So 5 to 9 we can choose. Yes, I think. Okay, they're not overlapping. So this is 5 to 9 is 4. And this 9 to 6 is 9 to 11. Okay, 9 to 11 is 2. Huh. So we got 5 for this. And after that, we are selecting 0 to 6. This is also overlapping. And all done, I think.
Yes, sir.
So one more is 9 to 11. 9 to 11 we have done. Okay. This 4 and so how many edges we have? 1, 2, 3, 4, 5, 6, 7, 8. We have created 5. So 3 should be, okay,
We
3 is
can
done.
take 5 to, no, 5 to 9 will not
No,
go.
no, done, done. Okay, so we have total 8 edge, and we remove 3, and now we are getting 5. Yeah, answer we are getting for in this way, this way correct. But we need some proof, so that will always provide the correct answer or not. So any counter example, we have to check this. Based on the difference value we can select or not. Okay, otherwise the solution is provided based on the finishing time. Okay, so finishing time, if you sort these activity uh, based on the finishing time in increasing order. Okay, and after that just start from the first activity and check, after sorting, just check the next activity is starting after the previous activity ending time or not, in that way. So 1 second, 2, 4, 6. This is in the sorted order, no? No, no, this is not in the sorted order. So for solve this problem, I am just creating the sorted order. So what is the sorted order based on the finishing time? So finishing time is first A. Okay, so I am writing 1 to 2, and next one is the 4 4. Okay, so 4. I can write B. So 3 to 4, and D is 1 to 4. Now next one is 5. Okay, E is 4 to 5, and F is, sorry, not F. Next one is 4 4 5 6. C. C is 0 to 6, and next one is 9 F. So F is 9 5 to 9, and G.
H, sir. H will be 8 to 10.
No, no, I'm just oh yes, correct. H
H is 8 to 10.
8 to 10, and G 9 to 11. Yes. In this way, first things we will sort our activity based on the finishing time. Okay. And after that, we will start the first activity, and then we will start selection. So first we will select. Okay. And to check the second activity, we will simply compare the start time with the previous finish time. If this start time of the next activity is equal to or greater than this previous finish time, then we can select. If this is smaller, then we will not select, we will ignore. Okay, so you can see this 3 is greater than 2, we will select this one. Okay, now D, this 1 is smaller than the previous finishing time, so we will not select this. And E, 4 is equal to this 4 previous one, so we can select. And C, 0 is smaller than, no. 5 is so previous last one finish time is 5. Okay, so this F, okay, so 5 is equal to 5. Okay, so we can select this. Now the last activity is finishing time is 9. So now H is starting time 8, which is smaller than 9, so we cannot select. Now the G is 9, which is equal to 9, we can select. Okay, we can simply traverse in the one loop, and we simply compare this start time with the previous activity selected activity finish time, and based on that we can count these numbers, so 1 2 3 4 5. So in this way we can get the correct answer for this problem, maximum.
Will it guarantee the optimal result?
Yes, yes. So I think sir have already proved this some by taking some scenario,
Okay,
and
sir.
okay, so this is actually guaranteed that you will get the correct answer in this approach.
What is this algorithm, sir?
Some steps actually, sir, just used by this graph things. So see similar type of this edge things.
So
Actually, sir.
we are just having start time, finish time, and we are just seeing like what things are matching. We are not really focusing much on how long those things are. Like we did like 116 and so on.
So we are starting from the finishing time. Okay, so this time if you start with the first time, okay, so 2. So okay, first finish time is 2.
Okay.
Okay, and we are performing one activity before this time. So definitely we have sorted this sequence in increasing order, so you will get the maximum activity if you select in this way. So next activity you are starting from if which is greater than or equal to this finishing time. Okay, so which is B, so suppose you are starting from this, next is 3 to 4. Okay, so in that way you overlapping you can easily remove, but for the guarantee things, for the maximize, okay, let me open the slides, sir. What example is given? Interval scheduling.
It's a proof by induction. Basically, we to see that
Yeah, actually,
by
sir.
removing one, just like we proved the DAG argument, right? If we remove a edge from a DAG, it will still remain a DAG, right? Same concept we have to apply here.
Yes. So actually, sir, mention some basic greedy approach. Pick the next booking to the allot based on the local strategy, and remove all booking. So some examples I have already taken. Some another approach I have already taken in this. Okay.
Yeah, we'll go through that, sir. Yeah.
Yeah,
So
this
because of
type of
quiz
counter
one,
example. Strategy
yeah,
one. Okay, so sir have discussed one strategy. Like this, choose the booking whose starting time is earliest. So based on this strategies are some give some counter example. Okay, so we are not getting the optimum answer. Strategy two, choose the booking spanning time the shortest interval. Yeah, which you mentioned that.
so
Okay,
that's
this one.
not a good strategy.
Okay, so this is also a not a
Good
good, and
strategy.
sir give some counter example for this also. Some, this is the strategy 3, strategy 4, and finally greedy algorithm for interest dealing. We have selected this another approach. Where is this? Yeah, this is actually, sir, discuss some counter example. One second.
So moral of the story is not only you have to be greedy, you have to be nice and greedy.
Hmm. A greedy algorithm and interval scheduling. Yeah, this algorithm is an action. So just go through once on the video, sir. Just give some example, okay, and just see that how, sir, actually this proved
So
by
this is
some.
actually applicable for our courses because most of the students who have overlap with subjects, right? There is usually a conflict with these live classes, right? So this is actually a practical problem. I don't know. We are using this to solve our or assign the slots. Hopefully,
Yeah. So you can see in the correct for the correctness, sir. Actually, this use this approach to fi and starting time like this. So currently, I am also not remembering the exact steps.
so we'll go through this. I think if there are any questions, that will bring up.
So
Yeah, that's a 2 hours needed. I think we're busy with quiz one, so now we have to catch up in next day or two.
yeah.
Yes.
Okay. So I'm just explaining the approach. Just visit one time this video. You will get the correction. This correctness part. Okay. And otherwise, we will discuss in the next session. Is not clear.
So you're talking about extra classes, sir, on Saturdays.
This time, okay.
So we should not be
Saturday.
neglected. I think we need now we are in the middle of what do you call a heap, right? So we need some time to revisit.
Oh,
You know,
he part.
no, no, I'm just saying like
Okay, no
our
problem.
stack is.
Actually, heap is also important
So
for the
I'm saying
quiz.
okay, maybe I was explaining. So our situation is like a stack is full.
Mhm. Yeah,
We have
okay.
been pushing a lot of stuff right now. Time to pop.
Yes. Okay,
Okay.
so I'm explaining the approach for the correctness part. We will discuss in next session. Okay, so just after discuss here, you can pause the video one time. Then, if you are not getting the things, they will discuss in the next. So for the next approach, this is one interval scheduling one topic. Okay, so here the solution is if we sort the our activity based on the finishing time, and then we can achieve get the answer, correct answer for the maximized selection. And another problem is also minimize lateness. So this is the another problem based on the greedy approach. So here one scenario is given: IIT Madras has single 3D printer. A number of user need to use this printer, but each user will get access to the printer but may not finish before deadline. Some deadline is also assigned for the each activity. Okay, so if any activity is completing before after the deadline, then we are just assigning the lateness value, how much time it is finishing at the late after the deadline. So we are assigning some value for the lateness. So
So it's
how we can
it's an
minimize.
optimization, right? With the Slack, right? You know what we learned.
Hmm.
Like we apply a Slack and you want to
Yes, correct.
minimize the penalty.
Penalty, yeah, penalty. You can see that. So we want to minimize this overall penalty. Okay, so suppose we have five activity like A, B, C, D, E, and some time is required to finish for each activity. Like this is required 2 hours, 3 hours, 1 hour, 6 hour, 5 hours like this, and one deadline time is also assigned. Okay, so like three at the time of three, this activity should be completed. At the time of four, this activity should be completed. Otherwise, some penalty is there. Okay, like this. So some deadline is also assigned. If we will start some selection schedule. Okay, we will select the activity in that way. So this our activity should be complete before the deadline. If it can complete, otherwise if it is completing after the deadline, we are assuming this is a lateness. Okay, lateness value. Suppose deadline is 4 and B activity is starting after 4 at time 5. So we can say that the what is the lateness value? 5 minus 4. So 1. Okay, finishing time minus deadline. So that is called the lateness value. So how we can reduce this lateness value for the all over the activity? Okay, so what will be the our order for the activity selections, so that this lateness value should be minimized. So that means suppose we are getting lateness value for A 0, B is 1, this is 3, this is 1, this is like 2. Okay, like this in that way. So here what is the maximum value among all? This is 3. So this maximum value should be reduced. Okay, our orders should be select in that way, so this maximum lateness should be minimum. Okay, maximum lateness among all the lateness should be minimum. So this is the main task here.
The min-max problem.
Min max
You are minimizing the maximum difference between scheduled
finishing time and deadline time.
actual achieved. So it's not a hard constraint. Like usually, this is a constraint for an activity, right? You must finish by this. Hard constraint means you will not allow any tolerance.
Yes.
We are
Here we are
softening the.
allow, but this lateness should be minimum.
Yeah.
It's more like a teacher is giving a deadline because they expect कि late होगा, but बहुत ज़्यादा late now. He's like एक दो दिन हो जाए, but
Yeah. So overall, if we identify the maximum of among all the lateness, okay, that value should be minimum.
So minimize the maximum lateness.
Okay, so this is the main goal for this problem. So first thing, the goal should be clear. So here example is given like this. One table is given, I think. Not given. Okay. So here you can see this job ID and this is given. Job ID and start time and finish time. Okay, where is the deadline? A second. So this job is given like, okay, so I'm just creating a table. So 1, 2, 3, 4, 5 and 6. And okay, so first value is the execution time, not the start time, execution time. So what time is required for the execution? So this is 3 and this is 2, this is 1, this is 4, this is 3 and this is 2. Okay, execution time. And last value is representing the deadline. So deadline is 6, 9, 8, 8, 9, 14 and 15. Okay, so this is the deadline. So we will start from the 0 time. Okay, so 0 time we will start and we will add this execution time and let's see when this is finishing. Okay, so now what order should we take to minimize this maximum lateness value? Suppose I'm taking in this given order, what value we are getting. So first we will run the first activity.
by like 136, what do we mean?
136, this first value is representing the ID only, activity
Okay.
ID. This is representing the execution time. Okay, how much time is required to complete this activity, and this is the time when deadline time.
Okay.
Okay, what time this should be complete. Okay, some deadline time. Okay, so we are starting at the 0 time. Okay, so suppose if I'm performing in the given order, so first activity is taking 3. Okay, so the finishing time is 3 and what is the deadline for this is 6. So that means we are completing our activity before the deadline, so lateness value is 0. Here we will not calculate the lateness as a minus value. Okay, lateness is we cannot take as a minus. We are finishing early, so that means we are not late, we are finishing at early only, so we will take 0 as a lateness. Okay, now next is after 3 we will start the next. So what is the execution time? 2. Okay, next activity execution 2 and finishing time will be 3 plus 2 is 5. Okay, now what is the deadline? 9. Same things, we are starting early, so lateness value is 0. Now next activity is taking 1, so we will perform 1 and finishing time will be 6 and deadline is 8. Same things, lateness will be 0. Okay, next we will add 4. So 6 plus 4 is 10. Finishing time. 1 second.
Late penalty of 1.
Okay, so what is the penalty of here? 1. And then 3. Okay, so 3 and we are getting 13 finishing time and 0. Okay, so 14, 0 here. And next is 2. So we are getting this 2.
0.
So
Just on
15
time.
and 15, yeah.
Just in time. Somebody just put the assignment under the door
4,
right on
3
time.
and 2 and 0. Correct. So what is the maximum among all?
1.
1. Okay. So if we change the order, so are we getting the same result or not? So order may be different if we change the order. So what should be the correct order? So this maximum among all the lateness should be minimum. Okay. So here actually we are, when we are performing in this order, we are giving 1. I think this is also an answer for this. So maximum lateness is 1 for this. But this order may be given in any random order. So if you just change the order, you will maybe find the different maximum value. Okay, here you are simply getting the correct answer. Uh, but this is not always the true. Okay, just change the order little bit. Suppose if I am performing this first activity like 4.
Make that 4th record the first one.
So I'm performing 4th, okay. And 4 I'm performing, so 0. So I'm starting from 0 and now finishing time is 4. Okay, so I'm writing ID here. Okay, so 4 ID I've completed. And the deadline will be, now this time I'm writing here a new one. So this is 0. Okay, now I'm performing 1. So 4 plus 3 will be 7.
Rate of 1 now.
Okay, so now we are getting 1 for this. And suppose if I am performing this 5th one, okay, then 5th one I am performing, this is the 1 and this is 5th one, and 7 plus 3 is 10. Okay, deadline is 14, so 0. Now I am performing 2. Okay, so you can see here this time 12. Okay, and deadline is 9 for this. So 12 minus 9 is 3. We're getting 3. Okay, then 3. So this is 2, and then 3. 1. So you will add 1. So 13. 13 minus 8 is 5. So you can see you are getting different this lateness value. So here you can see you are getting okay. So now 1 is remaining. So 13 plus 2 is 15. So this will 0. Okay. So you are getting maximum 5 this time.
So your strategy to guarantee optimal result, it should be independent of the order of the data, right? Then you know you have got a good strategy.
No, here this this is not the solution. I'm just taking random something, and in one random order I got the correct answer, but that is not the approach actually.
Correct.
Approach is if we sort these activity based on the deadline in increasing order. Here, if we sort these activity based on the deadline in increasing order, then you will get the correct answer, minimized this answer. Okay, so if you arrange all the activities 6, then 8, then 9, then 9, then 14, then 15. Okay, so then you will get definitely 1 maximum, minimum. Okay, and that will be the guaranteed optimum solution. Okay, so this is the another problem. Here we will sort the activity
Here
based
also,
on.
sir, we have a tie. Like for example, there are couple of them who could be the deadline could be the same, right? Here, of course, 6, 9, 8, 9, 9. There's a tie, right? The task number 2 and task number 4 are
Yes.
ending at 9, so there is a tie. Of course,
We can select any.
you can select any. Yeah, okay.
Yes, if we are selecting in that way, yeah. So in the previous approach, I think answer may be different. If we so this 2 and 4, if we change the order, then maybe you will get the different answer.
So it's not stable. I know I'm not using the right terminology.
Yeah.
So if it's, I mean, actually, there's a question like this in the quiz one, right? For insertion sort or something, right? Where the tuple was given, and then we had to sort it on the last one.
Yes, got it.
It reminded of that question actually. Yeah.
Okay.
Yeah.
So, but if we are performing after sorting, okay, so after sorting based on the deadline, if we are, if we can, then we can select any. Okay, if we are getting the same deadline, we can select any. So, in that way, you will get the correct optimum answer. Okay, but if you are selecting random order, then answer may be different. So this is the approach for this greedy approach. We will sort the activity based on the deadline, and then we will select in this manner. So this is the minimize lateness problem. And next one is the Huffman algorithm. Yeah, this one is the another algorithm, Huffman code, and this is actually used in the networking and this cryptography when we change the plain text into a ciphertext,
So it
one
is
form
taught
to
in
another.
some course, prefix coding. I don't know which course. Mad one.
Prefix.
Prefix coding.
Uh,
Mad one or DBMS? DBMS probably. Yeah. DBMS.
Prefix code. Okay, so maybe somewhere it is discussed. But yeah, prefix code we will discuss why
So it
we are
is,
using the terms
yeah,
prefix.
it was hash function or something. I mean, sorry, it was actually used for encoding, how to
Encoding. Yes.
compressing the data basically, right?
Yes. Yes. Correct.
Yeah.
Yeah. So Huffman algorithm is basically to compress the data and also encoding process. So we will simply convert a one form plain text form to the another form, maybe in bit forms or binary forms, and we also convert in that way. So total number of bits required, it is the minimum actually. So suppose I'm taking some example. If our message is created like A, B, C, D, E, these five characters. Okay, if our message is created using this five character, but the frequency is different for each character in our total message. Suppose this is repeating 100 times, this is repeating only two times, and this is repeating like 50 times, this is 40 times, and this is three times. Okay, so if we use the coding system where we are using the same length code for each character. Okay, so suppose I'm taking the 5 bits for each character. So 5, B for 5 bits, okay, C for 5 bits, D for 5 bits, and E for 5 bits each character. So definitely, how many total characters we have? We will simply multiplying by 5. Okay, so 100, 50, then 90, then 195. Okay, so 195 into 5. These are the total bits required for this message. If we have total frequency, this 100 plus 2 plus this in our message. So
So
now
there was actually,
how
there
we
was
can
some research done. Somebody analyzed all the English text and analyzed which words are most frequently used. I think it was letter E, T, A, O, something like that. So if you're doing that, then it makes sense to encode the most frequently occurring letter with the least amount of beat. So you want to give it a, like,
yes,
yeah, that was
yes,
like
yes, correct.
thought actually a later figure, Peter Norvig or something. Now I quickly recall this
Yes,
test.
yes, yes, correct. So here actually we want to encode this message by the minimum number of bits. Where the code will be different for each character, but not the same length code for the each character. Okay, so how we can generate the codes which are different from the each other, and the length of the which character which are repeating most number of times, that should contain the least number of bits, and which are repeating less number of times, that should contain the next number of bits. So overall you will get the minimum bits. So suppose if we assign like, so most frequent A is 100. Okay, so if we assign like 2 bits for this or 1 bit for this. Okay, and next one is the C. So suppose for C we are assigning 2 bits, and D we are assigning for 2 bits, and E and B we are assigning 3 bits, like. Okay, in that way length is different, but code should also be the unique, okay, for each character. Then how many bits we need to require. So for A, so 1 bit is required for A, so 100 is 100 into 1 plus 50 into 2. plus 40 into 2 plus, and this b 2, and both are 2, so we can see that 2 into 2 and 3 into 2, 2 into 3 and plus 3 into 3. Okay, so how many bits are required? So 100 plus 100 plus 80 plus 6 and 9. Okay, so approx 280, 295. Okay, but in the previous case 195 into 5, so definitely you will get approx 800 approx. Okay, or 900 plus. So how we can reduce the bits in the encoding systems based on the frequency of the characters? So we can create the codes using this Huffman algorithms, and it generate the codes based on this frequency information, and we can minimize the overall encoding bits requirement using this. So, and what is the approach actually? Okay, Huffman algorithm, how the Huffman algorithm works. So based on the frequency, we generate the tree. Okay, so I'm just taking the same example. Where is the example? Let's check. Okay, this one. So 100, 250, 40. Okay, I'm writing here. Okay, so A is 100, B is 2, C is 50, D is 40, and E is 3. Okay, now how we can create the codes, Huffman codes? So what's the algorithm is actually? So we create the Huffman tree in the bottom up manner. Okay, bottom up manner, we will create the Huffman tree, and every time we will select two node. Okay, we will select two node or two value from our current given weight frequency, and we will select minimum two value always, and we will create a tree. So initially we have these weight 2 and 3. Okay, so we will select the minimum 2 among all, 2 and 3, and we will start creating the tree from the bottom up side. So we will just make the leaf. So this is the actual frequency of character. So we will make these node as a leaf node. Okay, so I'm just maintaining, assuming this rectangle box as a leaf node. Okay, 2, and this is 3. Now we will create the sum of this. 2 plus 3 is 5. So in the next level we have now, I'm writing bits here, 100 and 50 and 40 and sum. Okay, so sum is 2 plus 3 is this is internal information. Okay, so 5. So 100 is representing A, and this C and this D, but this is representing by B plus E. Okay, so this is the internal node. So once again we will select two minimum. So what is the two minimum is 5 and 40, but 5 is already in our exist in our tree, and 40 will become a leaf node. Okay, so 40 we will assign with the with this internal node, and this is the actually character frequency, and we will once again create the no. Okay, so this is no 40, sorry, 40. So 40 and 5 is 45. Okay, now next sequence will be A100 and C50, and now we are getting overall sum 45 for this DBC. Okay, so I am just writing the internal node. Okay, so like this is internal node DB and E. Once again we will select two minimum this time, so 45 and 50. So 45 is already internal node, and 50 will become a leaf node. This is the actual frequency. So 50, and we will add this. Okay, so 95 we are getting. Okay, so we are getting 95 here, and now we have two value only remaining. Okay, we will select both. So 95 is the internal, and 100 will become leaf node. Okay, so 100. Now we will add this, and we are getting 195. So this rectangle box is actually representing the main frequency of character. So this 2 is for B, 3 is for E, 40 is for D, okay, and 50 is for C, and 100 for A. Okay, so this is the first step. We will create the Huffman tree. This is called the Huffman tree. and we are using the Huffman algorithm. This is greedy algorithm because every time we are selecting two minimum and we are creating using these two minimum. And the next step is Huffman codes. So how we can generate the Huffman code after creating this Huffman tree? So we will simply assign 0 value on the left edge and 1 value on the right edge. Okay, in the whole tree. So 0 1 0 1 0 1. Now for each character, okay, so for each character we will traverse from root to that character, and what edge value is coming.
So how did we get 195?
100 plus 95.
Okay.
Okay, so 195 we will add both, and 195 we are getting
So
finally.
we are starting from the least.
Yeah, so initially we have this sequence 100, 250, 40 and 3. So we will select first two smallest. First we will select two smallest, and we are getting 5. Okay, so 2 plus 3 is 5.
Hmm.
Okay, then the next remaining value is this 4, and we will add these both 5 plus 40. Okay, then we are getting 45 here. Then we have 3, so we will select two minimum 45 and 50, and we are adding 95, and then we are selecting last two, and we are getting 195. So in that way we are creating, but leaf node will actually contain the actual frequency of character in this tree. So after that we will assign 0 on the left edge and 1 on the right edge. Then you can traverse from the root node to any particular leaf node to identify the code. So suppose I want to calculate the code for A. So just start from the root node. Okay, so you have to traverse only one edge which have only one. Okay, so in this path, and this is the code for A. Now for B is at this position. Okay, last. So you have to traverse from root to this leaf. You have only one path. So 0 0 0 0. You are getting 0 0 0 0 for this B. And for C is exist here. So for to root to this C is 0 and 1. Okay, you are getting 0 and 1. And what is the D is here. Okay, so 40. So 0 0 1 0 0 1, and E is 0 0 0 1 0 0 0 1. Okay, so these are the Huffman codes, and length of this is 1, this is 4, this is 2, this is 3, and this is 4. You can see A have the highest frequency, have the smallest length. Okay, and B and E have the smallest frequency and the highest length. So our code is generating in that way. So these are called actually Huffman codes.
So the coding would be this 1000 and so on.
So if we want to send the message AC, then message will be A1, and then for C this is 01.
So if you're sending the message through that Morse code, you want to minimize minimum number of letters, right? Otherwise,
Yes, correct.
if you are doing UTF-8, for every letter you have to use 8 bits. I mean,
Yeah,
that's
that
too
things I
much.
have mentioned in the starting. The total number of bits required will be minimized in this way.
I also thought about Morse code.
Sir,
So
could you
this is
explain
like
how we
related.
got this 4 zeros for B, 0 1
Huh.
for C? I didn't get.
Okay, so from root node is this 195.
Yes,
Okay,
sir.
and we have assigned 0 on the left edge and 1 on the right edge for each. Okay,
Okay.
and for A, so where is the A? So A is this here.
Yes.
Okay, so to traverse from root to A, what sequence is coming on the edge, on the path?
1.
1. So because of that 1 we are getting here. Okay,
Okay.
for B is now this one. Okay, and from root to this B, what sequence are coming on the edge? 0 0 0 0.
Okay.
Okay, so this will be the code of B. And same for the C, you are getting 195 95 then 50. So this 0 and 1. Okay, in this sequence. So just check the path, what sequence is coming.
Okay. You have to check from the root.
Yes, from the root.
Okay, sir.
Okay,
That
so
root is basically some like of
huh,
the whole thing.
all the thing. and you are getting this Huffman codes, and these are the lengths. Okay, and one property actually these Huffman code is these codes are prefix code. Okay, so these codes are actually called as a prefix code. And what is the meaning of this? Actually, when we generate these codes, so code of any character cannot be a prefix of another code. Okay, you can check, code for any character cannot be a prefix of any other code. So if you see 1, if this a code 1 cannot be a prefix of any other codes. Okay, similar for C 01, you can see this 01 completely is not coming as a prefix in the another code. Okay, so these actually this property is coming in this Huffman codes.
So
Actually, so if you look at the first position, it will be one only for one letter. Like for A, the first position is one. For all other letters, it has to be zero. Otherwise, there'll be confusion when you're reading the file letter by letter. In the transmission, it will be confusion.
Yes,
So that is
yes.
uh,
Because of that, we can identify the correct code because code is not the coming as a prefix code in the another code, and this is happening because of this tree structures. Okay, we are always traversing the complete path. Okay, from root to leaf.
so what did you
Okay,
say
and
about the
each path
prefix?
is a unique path. Hmm?
What did you say about prefix code?
Actually, any code of any character cannot be a prefix of other codes. Prefix means if suppose this is the one code like 1101. Okay, this is the one code for another, and another character code is like 11. Okay, so this 11 you can see this is also coming as a initial part of another code completely.
Hmm.
Okay, so this code is actually coming as a prefix of another code. So this is not the case of Huffman codes. You cannot find any code which is a prefix of another code.
Okay, sir.
Okay, if this property is satisfying in this Huffman code, so we can say that these codes are prefix code actually. Yes, some definition is a little bit confusing. If this property is covering in this Huffman codes, we said that all these codes are prefix code overall. So Huffman code generate prefix code.
so we can take an example. If you write, let's say you received a file, now you have to decode, right? This is so. Let's say I receive a file containing 4 zeros. I mean, we don't know, right? Receive a bunch of binary digits, right? Four
Yes.
zeros. I mean, we know the answer, but let's say 4 zeros followed by one and then followed by 001. We decrypt. I mean, we received the message. Now we have to convert it into plain English using this Huffman code.
Hmm.
It's like a decryptive function, right? So somebody
Yes.
encrypted using Huffman encoding. Now we have to decode the message
Hmm.
to English, right? So then it'll be so it should not create confusion, right? When you're reading
Yes.
it,
Yes. Correct.
it should not create confusion. Is it what letter it is?
Hmm. So here, if I combine the code like 0 0 0 0 1, sorry 1 0 1 0 0 1, like this 0 0 0 0. So I've written this in randomly for. Still, you can easily decode this code. Okay, what is the procedure of decoding? You if you have Huffman tree for this Huffman codes, you can simply start the reading these bits from the initial part, and in the tree you can start traversing from the root node. Okay, and based on this value, just move accordingly. Okay, so if you are getting 0, just move to the left side. If you are getting 1, move to the right side from the current position. Okay, so suppose if you start from this first value 0, so in the original Huffman tree, one second, change the color. Okay, so from the first node, if you are getting 0, you will come here. Okay, and next 0 you are come once again you are moving here. Okay, so next 0 you are moving this position. At next 0 you are moving this position. At any time, if you are reaching at the leaf node, you will return a character. So this means you are getting the this after 4 traversing, you are getting B character. Okay, and after getting the character, just reset your pointer to the root node again. Okay, just move back to the root node and then traversing again. Okay, so for the next character 1 you are getting, just move to the this side. Okay, and you are reaching leaf node and you are getting A. So that means you are getting A. Okay, and once again next one reset again, and then root node, then you are getting 0. So once again move to the 0. Okay, and then 1, you are getting 1, so you are reaching C. Okay, and leaf node, just return the C. So in that way you can simply decode the message and you can get the actual message. Okay, so for this part you getting C. Next 001 you will get the D value, and next 40 you will get the B value, and you can easily decode. So because the code is prefix code, you will not confuse at any time by this prefix information. So you can get the actual correct text if your code is Huffman codes. Okay, so these are some property. Just keep in your mind this prefix property. So one question I am remembering that one quotes are given. Okay, so quotes, these Huffman quotes are given for some characters, and based on that this is asking that the code is Huffman code or not, possible Huffman codes or not, the valid codes or not actually. So based on this Huffman code, how you can identify that code is valid or not, you can simply check this prefix property, and if any code is prefix for another code, you can say that this is not a valid code. Okay, so one question I'm remembering that. Otherwise, some question is simply asked the to create the code for the frequencies. Some frequency is given or probability of the frequency is given, and based on this information, you need to just create the Huffman tree, and after that you can create the Huffman codes.
It was actually discussed, Shannon entropy. Like, so because you can convert the relative frequency divided by total, you'll get a probability distribution
Yes,
function,
probability.
right?
Yes, correct.
So you have a P log P. Shannon entropy was also discussed. Your
Mhm.
maximum length of encoding will be,
Yes.
yeah, that was also discussed. I mean, in another course, not here.
Mhm. Okay. Yeah, so this is the way of the Huffman algorithm concept of the Huffman, and this is also a greedy approach. And here some questions can be asked. So this is also important topic. Some mostly this frequency and when codes based question is asked, sometimes this validity of the codes asked based on this prefix information, so you can keep this in your mind time of learning. Yeah, so these are the topic which is covered in the week 7 of Mentry, and this is the last one,
So for OPP, is it covered like up to what week, sir?
week 9.
Week 9. Okay.
Yes, dynamic programming. Okay. So Max, this heap part is actually also important. So many question may be asked in the exam, many different type of questions based on the heap. So I'll check these things how when we can conduct the extra session for the topics. So what topics is required for the extra session is week 6 heap part, or any other topic from week 6.
Sir, also, I think we are revisiting the algorithm. I think one of the thing that Sir said is we can improve the order by changing the data structure, right? So we are kind of, that's why we are
Union kind
Ah,
of this type
yeah,
of activity. Okay.
yeah,
So last session you joined of the Bhaskar session.
yeah, sir. Yeah, it was a revision. No, yeah, we had joined last Wednesday. Yes.
Yeah, I think Bhaskar has discussed these two algorithm, how we can improve the Kruskal or the frames using union find data structure and heap. Okay,
Yeah.
so we will revisit again if we conduct the
So
extra
that's the
session.
whole idea of revision, sir.
Okay. So this Friday we will conduct the live coding, but after that we will check the schedule.
Maybe Saturday or Sunday. Saturday
Yes,
probably.
Sunday I think the OPP exam we have also busy in the duty. The
Saturday.
OPP exam. No, Sunday.
Saturday then, sir.
Yeah, Saturday we have to check.
Yes.
We have PDSA OPP in August, right?
Yes, after quiz 2.
Okay, okay.
Actually, it should be earlier so that the number of weeks will reduce.
Uh,
Oh my God, it's already plenty every week 9. I don't know. Uh,
What date is
It'll be a
the
torture, sir.
Yeah, 2 hours torture, huh?
what date is the OPP, sir?
Oh, someone is asking something very in very low voice. Who is this?
What date is the OPP, sir?
Date. Okay. You can find the date in grading document.
August 20 and August 27. There are 2 slots.
Yeah, 2 slots. You can choose any one. Okay,
But
and
the option is not really given now, right?
no, that will be open after the quiz 2 and before 1 week maybe of the OPP exam. But still, what we actually find that we always schedule the 50% student on the first date and 50% on the second date. But what happened when we ask to the student preference, so they actually choose the second date. Most of the students choose the second date. Okay, last
Yeah,
one.
because
Okay, so at that time we have to actually shift 50% only, and we have to reject the request for the remaining one.
So using
So
FIFO or LIFO method.
yeah.
but like logical would be to just choose the earlier date. I don't know.
Yeah.
Yeah, so
Yes, it's better to choose the earlier date.
yeah, you
Then you
want to
can
get rid of
focus on the actual exam, right?
you
Yes.
want
I
to be
can
get
prepare
it
for the
done with.
final exam then. Anyway, I don't think it'll be a great performance. Concept-wise, everything is okay, but while coding, I don't think it's easy.
when it comes to the implementation, the problem starts.
Yeah. If you're solving these grading assignments and then all PP assignment by yourself, I think you will not find this difficult.
So lot of packages are needed, sir. So we are going
Yes, sir.
back to week 3.
It's
Week
have
3
to
and
prepare
revising again
from
week
week
4.
5 now.
See, like
Yes.
sometimes the
Just
PPA
focus on the
assignments are tougher
algorithms.
than the graded assignments.
Yes, sir.
Just graph algorithms. Actually, graph algorithms are important for the one question in the OPP. Definitely, one question will come from the graph algorithm and one from the dynamic programming. Okay, and remaining two will come from another part.
What else is left, sir?
So only four problem we have.
So give some optional also. It doesn't matter, but anyway.